What would a star look like if it tried to hold itself together long after its fuel had vanished? If you're settling in for the night, or simply looking for something calm to drift along with, you're in the right place. Welcome to The Sleepy Scientist, and thank you for joining this quiet journey through the universe. Before we drift too far into the evening, there is something small and simple to ask. Where in the world are you listening from tonight? However far or close that place may be, it is lovely to have you here, and if you are new to the channel, a like and a subscribe would mean a great deal. It helps this little corner of calm science reach more people who might need it. If you are already subscribed, thank you, truly. And while you're here, you might like to tap the notifications bell, just so you do not miss the next bedtime exploration. There is a small chance tonight's story might be so interesting that it delays your sleep ever so slightly. But if that happens, at least you drift off a little wiser than before. So settle in, breathe softly, and let the day loosen its grip. Because just ahead lies the story of something astonishingly dense, remarkably small, and quietly powerful. And it invites a question worth pondering as you sink deeper into rest. How does a once brilliant star become something so compact that it could sit comfortably inside a single city, yet outweigh everything around it many times over? A star does not simply vanish when its fuel runs out. It transforms, sometimes in the most dramatic way that the universe allows, and before exploring the object that remains, it helps to understand what led it there. The introduction to neutron stars is not about explosions, despite the violence that creates them. It is about balance, collapse, pressure, and the strange kinds of matter that appear when nature pushes right up against its own limits. In this quiet moment, picture the life of a very large star. For millions upon millions of years, it burns through its fuel in a steady rhythm, its outward heat matching the inward pull of gravity. It seems eternal, but it is always counting down, always edging toward the moment when its fire will fade. When that balance fails, the star does not simply dim, it gives way. It folds inward. It collapses with such force that its very atoms are altered. This is where the story of neutron stars begins, not with the glowing ember of a dying sun, but with the sudden surrender of a giant. From that collapse comes an object so compact that everyday comparisons simply fall apart. A teaspoon of its material could outweigh mountains, and its gravity bends space with a firmness that borders on the unreal. In the chapters to come, the journey will move slowly inward, from the fading life of a massive star to the dense, quiet remnant it leaves behind. You will see its crust, its hidden ocean, its strange core, and the magnetic forces that twist around it like invisible storms. You will drift calmly past the physics that make these stars pulse, quake, cool, and collide. And little by little, the nature of these remarkable objects will become clear, the way details appear as your eyes adjust in a darkened room. So let the world go quiet for a while, and allow the universe to open gently. Because the story of neutron stars is not just a story of collapse, but of endurance. And it begins with a simple thought. What remains when a star refuses to fade without a final extraordinary act? A massive star begins its life with a kind of restless energy that never truly settles. From far away it appears calm, a steady point of light holding its place against the darkness, but up close its entire existence is built on speed. It burns through its nuclear fuel at a pace that would astonish quieter stars. Where a smaller star might stretch its life across billions upon billions of years, a massive star races forward, using up its supply of fuel in a fraction of that time. It shines brilliantly because it is living intensely, pushing out heat and light with a strength that announces its presence across great stretches of space. Deep within its core, fusion works tirelessly. Hydrogen is pressed together so tightly that it fuses into helium, and later helium becomes heavier elements. Every moment of this process releases energy. That energy pushes outward, creating a steady pressure that counters the enormous inward pull of gravity. Gravity wants to pull everything toward the center, squeeze the star tighter, draw every layer inward, but fusion holds it back. The star exists because these forces meet in a fragile balance, a perfect stalemate between collapse and expansion. For millions upon millions of years, the star maintains this equilibrium, like a worker who knows exactly how much effort is needed to keep everything running smoothly. But no supply lasts forever. Slowly, so slowly that the star itself might not recognize the change at first, its fuel begins to run lower. The core starts to feel the strain. Fusion becomes harder to sustain, and the energy that once pushed outward begins to falter. Think of a long shift nearing its end. The star has been working tirelessly, and though it still glows brightly on the outside, the weight of its own gravity is becoming harder to withstand. There is no dramatic signal at first, just a gradual weakening, a soft change in the rhythm that has held it together for so long. As the fuel dwindles, the core contracts slightly, heating up and trying desperately to spark new forms of fusion. The star begins fusing helium into carbon, and carbon into oxygen, then heavier elements still. Each step produces less energy than the last, and each step takes place over a shorter time. It is a little like burning through wood faster and faster, reaching for anything that might catch a light. But eventually the reactions stop providing enough outward pressure to hold gravity at bay. When iron begins to gather at the star's center, the real turning point arrives. Iron cannot be fused to produce energy. The process would consume energy instead of releasing it, and for a star this is the beginning of the true final stretch. The core reaches a point where no more outward pressure can be maintained. Gravity, which has been patient and persistent for the entire life of the star, finally takes control. The outer layers feel the shift almost immediately. The balance that once kept them suspended begins to break down. The star's long-standing routine has reached its final moments. There is no more fuel left to burn, no more reactions to push against the ever-present pull inward. The star has reached the end of its long shift, and gravity is ready to close the doors. The collapse that follows is astonishing in its speed. The core contracts in a matter of fractions of a second, shrinking as gravity tightens its grip. The atoms inside the star are crushed together with such force that electrons are driven into protons, forming neutrons. The structure of matter itself is rearranged under the pressure, as if the star's identity is being rewritten from the inside out. All the while the outer layers fall inward, accelerating toward the center in a massive rush. But before they reach the collapsing core, something remarkable happens. The core becomes so dense, so tightly packed with newly formed neutrons, that it suddenly stiffens. It stops shrinking. It pushes back. This moment is brief, violent, and transformative. The falling outer layers strike this rigid core and rebound outward in a roaring explosion that rips the star apart. The shockwave blasts heavy elements across space, scattering the products of the star's lifetime. The brilliant phenomenon known as a supernova is born from this single instant of resistance. What remains in the aftermath is not a gentle ember or a fading glow. It is something entirely different. A neutron star emerges where the core once stood, a remnant forged in the pressure of collapse. Its formation is dramatic and sudden, a transformation as intense as the life that preceded it. The outer layers have been cast away, but the core endures, smaller and unimaginably dense, carrying forward a new kind of existence. This is the surprising truth behind the death of a massive star. Its end is not a quiet dimming, but a sudden, powerful release, followed by the birth of one of the strangest objects in the universe. The star's long life of balance and burning leads, inevitably and beautifully, to this moment of unimaginable change. And as the dust of the explosion drifts outward, cooling and spreading across the cosmos, the neutron star remains at the centre, holding the memory of everything that came before in a sphere no larger than a city, yet heavier than mountains upon mountains. The journey of a neutron star does not begin softly. It begins in the heart of collapse, at the precise moment when a massive star reaches the limits of what it can hold together. And from that moment on, the remnant carries the story of pressure, gravity, and transformation in every particle compressed within it. When the last traces of fuel fade from the core of a massive star, the change is immediate and absolute. For millions upon millions of years, fusion has held gravity in check, creating a steady outward force that kept the star inflated and shining. But when that final spark of fusion falters, gravity wastes no time reclaiming its authority. It steps forward like a silent supervisor returning to a room that has grown too quiet, and everything within the star begins to move inward. The collapse begins almost instantly. Without the outward pressure of fusion, the core can no longer support even a moment of hesitation. The surrounding layers, which have been balanced for so long, suddenly feel a loss beneath them. They start to fall inward, pulled toward the core as though the scaffolding holding them in place has been removed. Gravity acts with an intensity that has been waiting patiently for this exact moment. The collapse is not slow, not gentle, and not spread across long stretches of time. It takes place in fractions of a second, so quickly that even the star itself might not understand what is happening before the change is complete. As the layers fall, the core is squeezed tighter and tighter. Matter has no choice but to obey gravity's pull. The space between atoms is crushed away. Then the atoms themselves begin to deform. Under normal conditions, electrons orbit protons with enough room to keep their structure intact. But in the collapsing core, the space they occupy disappears. Gravity pushes so fiercely that electrons are driven inward until they are forced into protons. The two merge, forming neutrons. It is as though the structure of matter folds in on itself, layers collapsing into a single, more compact form. This transformation is known in scientific language as neutronization, but here it can simply be understood as matter losing its familiar form. The building blocks that once arranged themselves into atoms with neat orbits and comfortable spacing surrender to the overwhelming pressure. The electrons and protons give up their separate identities and merge into something simpler and far more dense. Imagine a library where every book, instead of sitting neatly on a shelf, is suddenly compressed into a single, heavy volume. The information is still there, but the structure that once held it in separate forms has disappeared entirely. The collapse continues. What began as a sphere of ordinary matter is compressed into a far smaller shape. The density rises beyond anything found on planets, beyond anything found in white dwarf stars, beyond the imagination of any example drawn from daily life. A teaspoon of this newly compressed material could outweigh mountains, yet the collapse does not pause to acknowledge the boundary it has already crossed. Gravity continues to tighten its grip, pressing the matter into a form that resists further compression only when it reaches the limits of what neutrons themselves can withstand. Throughout this sudden and dramatic transformation, the outer layers of the star continue to fall inward. They crash toward the core, carried by momentum and gravity's relentless pull. The speed of their descent is astonishing, yet from the outside it would look like a single, smooth action. There is no pause, no slow motion, only an immense rush toward a shrinking centre that is being reshaped faster than the falling layers can realize. The entire star feels as though it is folding into itself, structure giving way to gravity in a show of power so complete that even the most massive layers cannot resist. Inside the core, the density reaches a point where neutrons themselves begin to press against one another so tightly that a new force awakens. This resistance is the final barrier that stops collapse from continuing unchecked. It is not something the star chooses or anticipates. It simply happens when matter becomes so dense that further compression requires more energy than gravity can supply. It is the last stand of structure within the collapsing star, the moment when the rush inward meets its limit. Before this resistance forms, though, the core has shrunk to a fraction of its original size. What was once a region spanning thousands of kilometers collapses into something not much larger than a single earthly city. Gravity performs this conversion with breathtaking speed, as though snapping a giant structure into a compact compressed form. The comparison does not fully capture the violence of the event, yet it helps bring scale to something happening too quickly to grasp. It is like watching a mountain compress into a pebble without slowing down in the slightest. The violence of this collapse is real, but there is also a strange kind of beauty in the efficiency of the process. The star has lived a life defined by balance, and now in its final moment that balance gives way to something entirely different. Matter that once floated freely inside the star surrenders its form, folding inward until only densely packed neutrons remain. Everything that once held shape and space is compacted into a simpler, heavier, more concentrated substance. The world outside the core has no time to understand what is happening within. The outer layers, still rushing inward, are racing toward a core that is changing by the millisecond. One moment they are falling into a shrinking, softening centre, and the next moment they strike a rigid sphere of neutron-packed matter that has reached its limit. The impact is extraordinary. The sudden halt sends a shockwave racing outward, and this shockwave becomes the spark that triggers the explosive release people call a supernova. Yet in the heart of this event, the collapse itself remains a story of surrender. It is matter giving up its familiar form. It is electrons and protons abandoning their separate states. It is structure folding inward until it becomes something new, something dense, something almost incomprehensible, and it all happens so quickly that the entire transformation could pass unnoticed if one blinked at the wrong moment. The collapse of a massive star is not a gentle fading, but a decisive end to the life it once lived. It is nature pushing itself to an extreme, reaching for the most compact form matter can take without slipping past the final threshold into a black hole. In this moment, gravity reveals its full strength and transforms the star's core into something entirely different from the vibrant structure it once held. And as the collapse finishes, As the shock wave begins to move outward, a new kind of object stands at the centre, silent and dense, waiting for the dust of the explosion to clear. The formation of a neutron star is inseparable from this collapse. It is born in the same instant matter yields to gravity and folds itself into something new. And from this moment onward, the story shifts from falling to enduring, from collapse to the strange, steady existence of a star that has given everything it had, only to rise again in a form far denser and far more unusual than before. When the dust and light of the supernova finally disperse, what remains at the centre is something deceptively small. After all the thunderous collapse, after the violent reordering of matter, the core that survives could be crossed on foot in an afternoon. A neutron star is astonishing not because of its size, but because of how little space it occupies. A whole stellar core is crushed into a sphere with a radius only a handful of kilometres across, small enough to fit comfortably inside a single city. You could imagine it sitting within the boundaries of a familiar place, the kind of distance you might drive across without thinking twice, and yet within that small space sits more mass than the sun. This contrast between size and mass feels almost contradictory. The human mind is used to associating big things with heavy things, and small things with lightness. A suitcase looks heavier than a pebble. A house feels heavier than a bicycle. But a neutron star refuses to follow those simple rules. It compresses so much matter into such a tiny space that the relationship between size and weight begins to dissolve. You could shrink such a star down even further in imagination, reducing it to the width of a street or a short walk, and it would still outweigh entire planets. The star has not lost its mass. It has only lost the room it used to occupy. To make sense of something so compact, it helps to picture distances you know well. Think of a city you can visualize easily, one with a handful of neighborhoods, a ring of roads, maybe a river cutting through the center. Now imagine that entire map being used as a container for an object heavier than everything around you combined. The scale feels impossible, yet it is real. A neutron star roughly the width of a city centre carries inside it the mass of a large star that once spanned millions of kilometres. All that volume is gone. All that material is squeezed inward until it forms a sphere far smaller than anything its original size would have suggested. The surface of a neutron star is only a few kilometres away from the centre, yet in those few kilometres the density rises from incredible to unimaginable. Even the crust alone is heavier and stronger than any substance on Earth. Beneath that crust the density increases by factors so large that comparisons begin to strain. A spoonful of neutron star material could outweigh mountains, not because it contains many objects, but because the particles inside it are pressed into one another so tightly that no space remains unused. Every part of the star is packed with extreme efficiency, as though nature has taken matter and folded it again and again until nothing more can be compressed inside its boundaries. To ground the idea further, imagine holding a smooth stone in your hand. It feels solid, reassuring and heavy for its size. Now imagine replacing the stone with something the same size, the same shape, the same feel under your fingers, but so heavy that you would not be able to lift it even a millimetre. It might look exactly the same, but its weight would pin your arm to the ground. That is the kind of contradiction at the heart of a neutron star. It looks modest in scale, yet its gravity and mass far exceed anything its size would suggest. This compactness changes everything about how the star behaves. Gravity near its surface is far stronger than even the strongest gravitational fields humans have ever imagined in earthly terms. If you stood on its surface, which is something no material body could ever survive, the downward pull would be so intense that it would crush anything instantly. Even light struggles, losing energy as it climbs away, stretching into redder wavelengths as it escapes. The power of gravity here is not proportional to the size of the object. It comes from the immense mass cramped into such a small space. The star's density also affects how quickly it can spin. Because so much mass is concentrated in such a compact space, a neutron star can rotate many times per second without tearing itself apart. The conservation of angular momentum makes it spin faster as it shrinks, the same way a spinning ice skater speeds up when pulling their arms inward. The result is a star that turns with incredible speed, sometimes hundreds of times in a single second. This rotation is as much a product of its compact size as it is a remnant of the momentum it carried from its earlier life. Even the surface of the neutron star reveals the consequences of extreme compactness. It is rigid, with a crust that is unimaginably strong, yet it covers a sphere smaller than a modest metropolitan area. Cracks in that crust, known as star quakes, send vibrations through the entire star, rippling through its dense interior in a way that would feel instantaneous if you could somehow sense it. The entire object is so cohesive that a tremor in one part shakes the whole structure. When thinking about density, it is natural to picture layers upon layers of material squeezed inward. Yet the reality is far more extreme. The particles inside a neutron star are pressed so close together that their identities blur. Neutrons pack tightly, one beside the next, forming a substance with no gaps or empty spaces. It is matter arranged in its most compact form, held together by forces that only reveal themselves when gravity has pushed past every previous barrier. A good way to appreciate this is to imagine reducing the space between buildings in a city. If every street narrowed to a line, and every building pressed directly against the next, the city would appear dense. Now imagine compressing the buildings themselves until they occupy the space of a single block, and then imagine compressing the material further still, squeezing the atoms into one another until the individual structures no longer matter. This is a rough comparison to what happens inside a neutron star. The outward size remains limited, but the amount of matter inside increases beyond anything a city or even a planet could ever contain. The difference between size and mass becomes essential here. A neutron star does not rely on volume to express its presence. It relies on density. It is like having the entire mass of a mountain range folded into something the size of a street lamp. You could walk past it without realizing what it contains, yet it would outmass everything in your surroundings combined. Its gravity would tell the true story, bending space around it, pulling objects with an intensity that seems out of place for something so small. And this compactness is what makes neutron stars such fascinating objects. They challenge intuition, asking the mind to hold two ideas at once: smallness and enormity. A star that once spanned millions of kilometers now fits comfortably within the borders of a single city, but its mass remains almost unchanged. The compression does not reduce the amount of matter. It simply removes the space that once allowed it to spread out. By understanding this scale, by placing a neutron star within a familiar framework, it becomes easier to appreciate the strangeness of what it has become. It is not merely a remnant of a once-living star. It is a new kind of object, defined not by its size, but by the intensity of its compactness. every centimetre inside it holds more matter than entire mountains. Every tiny area of its surface carries more weight than entire continents, and every moment of its existence is shaped by the density that defines it. This is the true scale of a neutron star, a city-sized sphere containing the mass of a star, small enough to picture, heavy enough to reshape the space around it, and compact enough to challenge the imagination each time the mind tries to grasp what it really means. Inside a neutron star, matter enters a realm where none of its familiar rules apply. The everyday world is made of atoms with generous amounts of space inside them. Electrons orbit their nuclei at distances that seem large when compared to the size of the particles themselves. Most of what is considered solid is, in truth, mostly empty space. Tables, rocks, metals, skin, clouds, mountains, oceans, all rely on atoms behaving in predictable, spacious ways. But under the immense pressure inside a neutron star, this arrangement cannot survive. Gravity pulls so fiercely that the usual spacing between particles collapses, and the structure of matter folds in on itself until almost nothing of its old identity remains. Imagine an atom the way it is often described, a tiny nucleus at the centre with electrons moving around it at relatively large distances. Now imagine those distances shrinking, drawn inward by an irresistible force that leaves no room for these orbits to exist. Inside a neutron star, this is exactly what happens. The outward push that usually keeps electrons in place disappears under extreme pressure. They are forced inward until they merge with protons, creating neutrons. The atom, as it is known, ceases to be an atom. Its components are still present, but not in their familiar arrangement. The empty space that once defined most of its volume is gone, replaced by a dense packing of particles in direct contact. What emerges from this transformation is matter of a kind the human mind has no direct experience with. It is neither gas, nor liquid, nor solid in any earthly sense. It is a dense crowd of neutrons squeezed together so closely that they form something like an enormous star-sized atomic nucleus. Every neutron sits next to its neighbours with almost no room between them. They cannot be compressed much further without breaking into even more exotic states. This tight packing is supported by a resisting force known in physics as neutron degeneracy pressure, but here it can be thought of more gently as the stubbornness of neutrons refusing to be pushed any closer together. In everyday life, pressure means something like squeezing a sponge or compacting soil. Even in extreme environments on Earth, such as the crushing depths of the ocean trenches, the pressure is nothing compared to what exists inside a neutron star. There, pressure becomes a force so intense that the particles themselves push back, not out of preference but out of fundamental necessity. Neutrons behave like people crowded into a space so tightly that no one can move or bend, and the group as a whole resists any attempt to make the space smaller. This collective resistance is what prevents the neutron star from collapsing further under its own weight. Inside this dense environment, matter loses every feature that makes it familiar. There are no atoms with orbiting electrons. There are no bonds linking elements together. There are no molecules forming fluids or solids. It is matter reduced to its simplest form, arranged in a way that only extreme gravity can enforce. If one could somehow dip a hand into this interior, which of course no material hand could survive, it would not feel like anything known. It would not be hot or cold, soft or hard, liquid or rigid. It would be something beyond comparison, a state of matter formed under pressures so great that language struggles to keep pace. To picture it more gently, you might imagine trying to compress a pile of soft, fluffy pillows into a tiny box. At first, they squeeze and crumple without complaint, but eventually the pillows are pressed so tightly that they cannot be compressed further without tearing apart the fabric itself. In a similar way, the matter inside a neutron star reaches a point where it cannot be squeezed further without breaking down into something even stranger. The neutrons hold their ground, resisting gravity's push with everything they have. The density also changes the way waves and disturbances travel through this material. In normal solids, vibrations move at speeds that depend on the stiffness of the material. In a neutron star, the stiffness is so great that disturbances pass through almost instantly. A ripple at one point of the star can be felt across the entire structure before a blink of an eye. It is as if the star behaves like a single, unified piece of matter, with no gaps or weaknesses to slow movement. Soft imagery can help ground this concept. Imagine a bowl filled with marbles, each marble touching its neighbours. Now imagine shaking the bowl. The marbles shift and push against each other, each one passing the motion onward. This is somewhat like how vibrations travel through neutron star matter, but at speeds and intensities far beyond anything the marbles could ever manage. Or picture a sponge soaked with water, the openings between its fibres filled completely. Then imagine squeezing the sponge until no holes remain. That final, holeless sponge still has far more empty space than the interior of a neutron star. But the image hints at how matter behaves when no room is left at all. As matter is pushed into this state, it stops behaving individually and becomes part of a larger whole. Neutrons do not float freely or interact lightly. They press against one another with constant force, forming a structure defined entirely by pressure. Even the concept of a surface begins to blur. A neutron star has a crust, yes, but beneath that crust the transition into the dense interior is smooth, with no clear boundary between one region and another. Everything blends together into a continuum of increasing density, each layer shaped by the immense gravity pressing down on it. This raising of density to unimaginable levels also affects the star's gravity. The more compact the matter becomes, the stronger the gravitational field surrounding it. Near the surface, gravity becomes intense enough to bend the paths of light passing by. A photon leaving the surface loses energy as it climbs out of the gravitational well, becoming redder as it escapes. Even time passes differently in this environment, slowing near the surface compared to a distant observer. All these effects arise simply because matter is squeezed so tightly that gravity has room to express itself more fully. The deeper one goes into the interior, the more abstract the concept of matter becomes. The neutrons behave less like particles and more like a continuous fluid, one that flows without friction under certain conditions. This strange behavior hints at deeper mysteries that scientists still try to understand. Even with all that is known, the exact nature of matter at the deepest layers of a neutron star remains uncertain. Some theories suggest that neutrons themselves may dissolve into their constituent quarks under enough pressure. Others propose the formation of entirely new kinds of particles. No laboratory on Earth can recreate such conditions, so the true story remains hidden behind the star's dense exterior. But despite all this strangeness, the principle is simple. When matter is placed under extreme pressure, it changes. It lets go of the structures that made it familiar and enters a state dictated entirely by the forces surrounding it. Inside a neutron star, this process is taken to its limit. Everything is compressed, unfolded and shaped by gravity until it reaches the densest form nature allows. The result is matter that behaves in ways impossible to imagine in everyday life. A kind of cosmic material whose properties emerge only when pressure becomes overwhelming. The interior of a neutron star is a place where matter has surrendered its identity. Atoms are gone, electrons are gone, space itself seems to disappear. What remains is a dense, packed assembly of neutrons held together by gravity and the resistance of the neutrons themselves. It is matter at its most extreme, shaped not by temperature or chemistry or form, but by the universal tendency of gravity to pull everything inward until nothing more can be compressed. This is what it means for matter to exist under extreme pressure, a state where the rules change, the familiar dissolves, and the fabric of matter becomes something entirely new. The surface of a neutron star is a strange contradiction. It is the outer skin of one of the densest objects in the universe, yet in thickness it is only a small fraction of the whole. If one could somehow approach it, the first layer encountered would not look like anything familiar. It would not resemble rock, metal, ice, or any other substance known from planets and moons. Instead, it would be a crust made of highly compressed atomic nuclei arranged in patterns as rigid as any structure nature can create. It is a solid that should not exist under ordinary circumstances, because the pressure holding it together would tear apart any earthly material long before it even formed. To imagine this crust, it helps to begin with the idea of a lattice. On Earth, metals and minerals often arrange themselves in ordered structures, with atoms sitting in repeating patterns. In a neutron star, the same idea exists, but taken to an extreme. The nuclei are squeezed so tightly that electrons are stripped away, leaving behind a sea of free electrons drifting between densely packed nuclei. The result is a kind of crystalline arrangement, where the spacing between nuclei is far smaller than anything in terrestrial matter. The pressure is so immense that the crust becomes incredibly strong, more rigid than steel, diamond, or anything humans have ever engineered. If one were to compare a piece of neutron star crust to the strongest material found on Earth, the difference would be almost laughable. Steel bends and flexes under stress. Diamond, though famously hard, can fracture under sharp impacts. Even the toughest alloys cannot withstand high temperatures or pressures without deforming. But the crust of a neutron star holds its shape under conditions that would crush, melt, or vaporize any earthly substance instantly. It is held together by nuclear forces acting on a scale that dwarfs anything seen in minerals or metals. A crack in this crust would require stresses so enormous that they would be unthinkable anywhere else. Even so, the crust can crack. Despite its strength, the forces surrounding a neutron star push it constantly to its limits. Its rotation can be extraordinarily fast, and the centrifugal effects tug at the rigid surface. Its magnetic fields, often trillions of times stronger than Earth's, twist and pull the crust like invisible ropes. These stresses accumulate slowly, like tension building in a steel beam under too much strain. Eventually a fracture forms, releasing energy in a sudden, sharp event known as a starquake. The crust snaps, shifts, or adjusts, and the energy released can travel through the star with extraordinary speed. To picture the crust more gently, imagine walking on a frozen lake. The ice beneath is solid, smooth, and cool, but underneath lies water that shifts and moves. On the neutron star, the ice is stronger than anything imaginable. and the material beneath is not water, but a dense, flowing mixture of neutrons and exotic particles. The crust is incredibly thin relative to the depth of the star, perhaps no thicker than a few kilometers, but it plays a critical role in the structure of the neutron star. It is the boundary between the outside world and the extreme interior. At its highest layers, the crust contains nuclei of heavy elements arranged tightly in a pattern. These nuclei might resemble elements found in the periodic table, but they are distorted by pressure into shapes that could not exist under lighter conditions. As one moves downward, the pressure increases sharply. The nuclei begin to change, their shapes elongate and stretch. Eventually, at even deeper layers, they can form structures nicknamed after familiar objects: rods, sheets, and even bubble-like formations. These shapes are not literal, but serve as soft metaphors for how nuclear matter rearranges itself under rising pressure. Scientists sometimes call these phases nuclear pasta because of the playful resemblance to spaghetti, lasagna, or gnocchi, but the reality is far more extreme than the gentle imagery suggests. Below this region, the density becomes so high that nuclei and neutrons blend together, forming a mixture where the distinction between one and the other starts to blur. The transition from the crust to the deeper layers of the neutron star is not a sharp boundary, but a gradual shift. Nuclei become heavier and more deformed. Neutrons drip out of their boundaries, and eventually the crust fades into a superdense interior where neutrons dominate. The crust is also responsible for several unique behaviors of neutron stars. Because it is rigid and solid, it can store rotational and magnetic stresses, releasing them suddenly in events that astronomers detect as changes in the star's spin or bright flashes of radiation. When the crust cracks from stress, the star's rotation can speed up slightly, creating what is known as a glitch. This might seem counterintuitive, but the explanation lies in how the interior fluid and the solid crust interact. The crust can shift suddenly, transferring angular momentum and causing the star to spin more quickly. Comparing the crust to earthly rocks or minerals helps reveal just how extreme its properties are. Granite, basalt, and diamond all have limits to the pressure they can endure. Even at their strongest, they rely on bonds between atoms spaced at comfortable distances. Those bonds break when pressed too tightly. But in the crust of a neutron star, the atomic spacing is almost non-existent. The nuclei are pressed so close together that they cannot move or rearrange easily. The crust behaves like a continuous, unyielding shell, strong not just because of the material itself, but because of the pressure pressing it together. Visualizing this can be challenging, but imagine holding a piece of metal so stiff that it does not bend even a fraction when struck with tremendous force. Now imagine that force multiplied by millions upon millions, and the metal still refusing to give way. That level of rigidity hints at what the neutron star crust is like. It is a place where matter clings to its structure even as gravity pushes inward from above and deeper layers push upward from below. Despite its strength, the crust is incredibly thin compared to the total volume of the neutron star. If the star were the size of a standard globe, the crust might be no thicker than a sheet of paper wrapped tightly around it. Beneath that delicate outer layer lies the dense interior, which behaves more like a fluid than a solid. This contrast creates tension at the boundary, which is one reason cracks and shifts occur. The combination of a rigid shell over a fluid interior is inherently unstable, especially under the forces generated by intense magnetic fields and rapid rotation. The crust also plays a role in how the neutron star emits radiation. Charged particles near the surface interact with magnetic fields, creating beams of high-energy light that sweep across space if the star rotates. The rigidity of the crust influences the stability of these beams, allowing pulsars to tick with remarkable regularity. A single crust fracture, however, can alter the star's magnetic field or adjust its spin, changing the pattern of pulses that astronomers observe. Understanding the crust helps ground the entire concept of a neutron star. It reminds us that even at the outermost edge, where one might expect something familiar, the physics is radically different. The crust is the most normal part of the neutron star, and yet it is more extreme than anything on Earth. It is a solid formed in conditions so intense that no experiment can reproduce them, a thin shell protecting a world of unimaginable pressure beneath. And while it is strong beyond comprehension, it is also vulnerable to cracks and shifts that release staggering amounts of energy. It is both rigid and delicate in its own way, a paradox shaped by gravity and nuclear forces. This thin outer layer stands between the vacuum of space and some of the strangest matter in the universe, a reminder that even the surface of a neutron star is extraordinary in every possible way. Beneath the rigid crust of a neutron star lies a region where familiar ideas about matter begin to dissolve. As one descends through this boundary, the solid lattice of nuclei gradually gives way to something far stranger, an inner ocean unlike any liquid found on Earth. It is a sea of neutrons packed so closely together that the distinction between fluid and solid becomes blurred. This ocean is not made of water, nor of molten rock, nor of any kind of earthly substance. It is matter rearranged by gravity into a state so dense that ordinary comparisons fall short. Yet gentle metaphors can help build a bridge to understanding. Imagine standing above the surface of a calm, dark ocean on a moonlit night. The water looks still from a distance, yet beneath the surface countless currents move quietly, shifting with slow, powerful grace. In the inner layers of a neutron star, the water is made of neutrons rather than molecules, but the behavior has a similar quiet motion mixed with an unbreakable density. Neutrons drift and flow past one another, but they are packed too tightly to fit typical notions of liquid. Instead of swirling freely like water, they move in a collective, organized way, more like the grain in a block of wood or the texture inside a crystal, yet fluid enough to slide and shift when conditions demand it. This combination means that matter here behaves both like a liquid and like a solid. It can flow without friction, but under certain circumstances it can also resist deformation with remarkable strength. This paradoxical behavior creates an environment that is both flexible and firm. As one moves deeper from the crust into the inner ocean, the density increases gradually. Neutrons press closer and closer, and the fluid becomes more cohesive. There is no sudden transition, no sharp line between one phase and the next. Everything moves in a smooth descent, the pressure rising with every passing meter. The density at these depths is incredible. A cubic centimetre of this matter would outweigh mountains, and yet it behaves with an elegance that does not reflect its weight. If one imagines scooping up a handful of this neutron fluid, although no human hand could ever survive the attempt, it would not behave like any familiar substance. It would not splash or ripple like water. It would not pour like molten metal. Instead, it would flow in a silent, unified wave. its motion guided not by the push of individual particles, but by the harmony of countless neutrons acting together. This behavior hints at one of the most unusual properties of the inner ocean, superfluidity. In everyday terms, a superfluid is a liquid that flows without friction, moving endlessly without losing energy. On Earth, superfluidity occurs only under very specific conditions, usually at extremely low temperatures close to absolute zero. In a neutron star, it arises not from cold, but from density and pressure. The neutrons arrange themselves into a state where they move collectively, as if sharing a single unified rhythm. They slip past each other without resistance, gliding through the star's interior with perfect smoothness. To picture superfluid movement, imagine a river that never slows down, no matter how many bends it takes or how much distance it covers. The water would glide and turn with no turbulence, no drag, no hint of friction. In the inner ocean of a neutron star, this impossible river becomes real. Neutrons move through the core with a singular grace, obeying laws that only reveal themselves when matter is pressed to its limits. Yet despite the dreamlike nature of this fluid, there remains an underlying solidity. The neutrons are so densely packed that, although they flow freely, they also contribute to a collective stiffness. If a ripple or wave begins in one part of the star, it can travel through the entire interior almost instantly. The fluid responds as one, its structure allowing disturbances to propagate with incredible speed. It is as if the entire inner ocean is a single, unified substance, rather than a collection of countless particles. As one imagines descending deeper, the pressure increases steadily. The neutrons become more orderly, more tightly pressed together. The crust above gives way completely, leaving only this vast ocean of dense matter stretching down toward layers that grow stranger with each passing kilometre. The landscape here is smooth, uniform, and devoid of the chemical diversity found in normal environments. There are no molecules, no minerals, no gases, nothing that behaves independently. Everything is part of a continuous fluid that bends and flows under forces unimaginable in everyday life. To keep the mind grounded, it helps to compare this fluid to familiar earthly materials. Picture honey poured slowly into a bowl. It moves thickly, resisting at first, but eventually it settles and spreads in a smooth sheet. Now imagine something with the smoothness of honey but the firmness of a polished stone, capable of flowing with silence yet resisting compression with strength far beyond diamond. This hybrid behavior captures a hint of what the neutron fluid is like, though the pressure inside the star makes everything far more extreme than honey or stone could ever express. The transition from the crust to the inner ocean is gradual but profound. Higher up, the nuclei still cling to shapes, arranged in crystalline patterns. As the pressure increases, these shapes melt away. Neutrons begin to spill out of the nuclei, joining the sea around them. Eventually, the nuclei themselves dissolve, leaving behind a continuous fluid. This transition can be imagined as ice melting into water, but instead of warmth causing the change, it is pressure compressing the particles until their individual identities dissolve into the collective whole. This inner ocean is also essential to the star's long-term behavior. It carries heat away from the deeper layers, allowing the star to cool slowly over time. It influences how the star rotates, interacting with the crust above it, and transferring angular momentum in subtle, complex ways. When the crust suddenly shifts or cracks, this fluid responds, sometimes creating sudden changes in the star's rotation, known as glitches. These interactions show that the crust and inner ocean are deeply connected, each shaping the behavior of the other. As one moves even deeper into the ocean, toward the mantle of the neutron star, the composition becomes more uniform. Neutrons dominate, but small numbers of other particles lurk among them, squeezed into existence by the intense pressure. Protons and electrons, though rare, drift through the fluid, carried along by the flow of neutrons. They contribute to the star's magnetic behavior, responding to fields that thread through the interior. Their presence is subtle but significant, hinting at the complexity beneath the simple idea of a sea of neutrons. This ocean extends down to depths where the density approaches that of atomic nuclei. At these extreme pressures, the neutrons begin to interact in ways that approach a more exotic state. The fluid becomes stiffer, more cohesive, more unified in its motion. It is easy to imagine this place as silent and heavy, yet incredibly active beneath the surface. The currents here do not resemble rivers or tides, but move with a purpose tied to the internal structure of the star. Seeing this environment through gentle metaphors helps make sense of something so extreme. It is an ocean, but not of water. It is a fluid, but not of any familiar substance. It flows, but without friction. It supports weight, but without behaving like a solid. It exists only because the pressure inside a neutron star overwhelms everything else, reshaping matter into a form that reveals the hidden flexibility of particles under stress. Descending through this ocean reveals the wonder and complexity of neutron star interiors. It is a place where matter behaves in dreamlike ways, flowing, shifting, and responding to forces that no earthly environment could replicate. Even though it is one of the densest places in the universe, the fluidity within it gives the neutron star a surprising kind of grace, a smooth and continuous movement that belies its immense weight. This inner ocean is the bridge between the crust above and the strange core below. It is the region where matter learns to move without resistance, where density and pressure reshape every particle into part of a fluid whole, and where the star's hidden rhythms begin to reveal themselves. Deep within the neutron star, below the dense crust and the vast inner ocean of neutrons, lies a region where the laws of matter reach their most mysterious form. This is the core, a place so extreme that even scientists who study it every day admit they are working with educated guesses, models, and possibilities rather than certainties. The pressures and densities here rise far beyond anything that can be recreated in experiments on Earth, leaving the core one of the universe's most intriguing secrets. To understand it, the imagination must move gently, guided by what is known while accepting the vastness of what remains uncertain. As one descends toward the core, the density increases steadily. The superfluid ocean above grows thicker, more coherent and more deeply unified. Neutrons that once glided freely begin to interact more aggressively, packed so tightly together that their behavior changes. The deeper the descent, the greater the pressure, rising to levels that approach the limits of what physical matter can endure. At these depths, gravity compresses the interior so intensely that the neutrons themselves begin to feel the strain. Their identities as individual particles begin to blur. One of the central ideas explored by scientists is that the core may contain superfluid neutrons so dense that even their unusual behavior in the inner ocean becomes mild by comparison. In the core, these neutrons may join into a single collective state, moving with perfect smoothness. This idea suggests a substance with no analogy in the everyday world, a kind of matter that does not break, crack, or resist the way solids do, nor flow turbulently like liquids. Instead, it glides, unified and silent, its motion defined by pressures far beyond any normal experience. But the certainty ends there. The pressure at these depths becomes so great that some scientists wonder whether neutrons can even survive intact. Neutrons are made of smaller particles called quarks, bound together by strong forces. Under extreme pressure, those forces might weaken or transform, allowing the neutrons to dissolve into a fluid of quarks themselves. This hypothetical state, known softly here as quark matter, would be a soup of fundamental particles, stripped of their usual structures and free to flow in ways even stranger than the neutron superfluid above. To imagine quark matter, picture a landscape of grains dissolving into fine powder, and then imagine that powder dissolving further into a mist so fine that the granules no longer have edges. This mist moves as one, losing any sense of individual pieces. In a neutron star core, this mist would be made not of dust or droplets, but of the most fundamental particles known, floating in a dense, featureless sea. This idea hints at matter stripped entirely to its essence, a state where the familiar building blocks of atoms no longer exist. Another possibility involves hyperons, particles heavier than neutrons that appear only under extreme conditions. Hyperons may form when neutrons are squeezed tightly enough that their internal structure rearranges itself. These particles have strange properties and may appear briefly or persistently depending on the pressure. Their presence would change the stiffness and behavior of the core, altering how the neutron star vibrates, rotates, or cools. But because hyperons have never been observed under the exact conditions found inside a neutron star, their role remains a subject of ongoing curiosity. The difficulty in determining what lies within a neutron star core arises from the impossibility of recreating such conditions in a laboratory. No machine on Earth can produce pressures even remotely comparable to those in the center of a neutron star. Even the most powerful particle colliders, which smash particles together at enormous energies, only mimic tiny bursts of extreme density, lasting fractions of a second. These glimpses are helpful, but they cannot offer a full picture of what happens deep inside a neutron star core, where the conditions are steady, continuous, and unimaginably intense. Because of this, scientists rely on indirect clues. They study the star's vibrations, rotation, cooling rates, and responses to magnetic stress. They examine the behavior of neutron star collisions and the gravitational waves those collisions produce. Each piece of information offers a small hint, a whisper of what the core might be like. But the complete story remains out of reach, hidden behind the impenetrable layers of the star itself. The pressure within the core is so intense that even metaphors struggle to capture it. One might imagine stacking mountains on top of one another until their combined weight begins to crush the ground below. The pressure deep beneath those mountains would be great, but in a neutron star's core the pressure is far greater still. Or picture trying to compress an iron ball the size of a house into the size of a pebble. The rigidity of iron would resist, but even that resistance would be hopeless against the gravity inside a neutron star. The core exists at the point where all resistance has been overwhelmed, leaving matter in a state dictated solely by pressure. Metaphorically, one might consider the core as a place where matter has been stripped down in layers. In the crust, nuclei remain. In the inner ocean, neutrons drift together. But here, in the core, even the concept of an individual neutron may fade. The deeper one goes, the more matter seems to lose its identity, becoming a thick, uniform soup. If each particle were once a bead, a pearl or a grain, in the core they are dissolved into a smooth mixture where no boundaries remain. Everything flows into everything else, shaped by pressure rather than by chemical or nuclear bonds. This soup-like nature does not imply chaos. It suggests a deep, calm uniformity. Matter pressed to its essence forms a stable state, even if it is one rarely seen in the universe. Neutron stars contain these cores not because matter prefers to exist this way, but because gravity leaves no alternative. When the pressure becomes too great for atoms, they collapse into neutrons. When the pressure becomes too great for neutrons, something else emerges, something that cannot exist outside these extreme environments. The behavior of the core influences everything above it. Heat produced here travels slowly outward, cooling the star over long cosmic timescales. Vibrations originating in the core ripple upward and can be detected across the star's surface. The core determines how stiff or flexible the star is, shaping the speed of waves that travel through it. Even the star's rotation depends partly on how the core responds to changes in angular momentum. Thinking gently about this region helps maintain a sense of perspective. While the core operates under conditions impossible to imagine directly, its behavior follows the same physical laws that govern particles everywhere. Forces act, particles respond, and structure emerges. The difference is one of scale. In the core of a neutron star, those laws operate with pressures and densities so high that matter explores possibilities closed off elsewhere. To picture this region in softer terms, imagine a sphere at the centre of the star, glowing faintly with trapped heat, its surface smooth and uniform like a polished stone. Now imagine that this sphere is not a solid object, but a fluid that behaves like both a solid and a liquid at the same time, a substance that flows seamlessly, yet resists compression with unimaginable strength. Inside this sphere, particles drift not as individuals, but as part of a unified whole, like dancers moving in perfect synchrony, their identities dissolving into the collective motion. This is the essence of a neutron star core, a place where matter is pressed past every familiar boundary, where particles rearrange themselves into states that challenge understanding, and where the universe's laws reveal their hidden depths. It is a realm of quiet extremity, silent and dense, containing the strangest material known, or perhaps not yet known. And as the layers above shift and move, the core endures, holding the star together in ways that defy everyday intuition, while remaining perfectly natural under the immense weight of gravity. In this deepest region, matter has reached the end of its journey. It cannot collapse further without becoming something even more radical, something that only happens when gravity grows strong enough to create a black hole. Until that threshold is crossed, the core stands as a monument to pressure, density, and transformation. It is matter stripped down to its most essential form, held together by the universe's most powerful force, and existing in a quiet, mysterious state that continues to captivate anyone who wonders what the heart of a collapsed star might truly be. The space surrounding a neutron star is shaped by gravity so intensely that the familiar rules of distance and motion begin to bend. Gravity is something felt every day on Earth, a steady pull that keeps feet on the ground and oceans in their place. It is dependable, predictable, and gentle. Even in dramatic places like mountain cliffs or deep ocean trenches, gravity feels constant, never revealing the full range of what it can do. But near a neutron star, gravity shows its strength openly. it becomes so powerful that space itself curves, time slows down, and light must struggle to escape. To understand the gravity near a neutron star, it helps to imagine standing on the surface of Earth and trying to jump. The force pulling downward is strong enough to keep everything anchored, yet gentle enough that a small leap is possible. Now imagine increasing that downward pull, not by double or triple, but by factors so large that numbers begin to lose meaning. If the gravity near Earth were a calm tug, the gravity near a neutron star would be a vast, unyielding grip. Standing on the surface of such a star which nobody could survive, the pull downward would be so intense that lifting even a fraction of a millimeter would require impossible strength. Even light, which normally zips away freely, loses energy as it climbs out of the star's hold. This loss of energy in light is known as gravitational redshift. To picture it gently, think of light as a traveller climbing a steep hill. As it climbs, it becomes tired, losing some of its energy along the way. For light, losing energy means shifting toward redder colours. If one were to watch light leaving the surface of a neutron star, it would arrive looking stretched, softened, its colour shifted by the effort of escaping such intense gravity. This stretching happens not because anything is wrong with the light, but because the gravity near the star is simply too strong to let it leave without some cost. Another way to appreciate the star's gravitational strength is to imagine the path of time itself. On Earth, time flows steadily, the same from moment to moment no matter where one stands. But near a neutron star, time slows down. A clock placed near the star's surface would tick more slowly compared to an identical clock far away in empty space. This difference would not be noticeable to the person holding the clock, but to a distant observer it would be unmistakable. The closer one moves toward the neutron star, the more time stretches, and the more the familiar flow of seconds begins to drift. This slowing of time and bending of space is a sign that the neutron star sits close to the edge of becoming something even more extreme. A black hole represents gravity pushed to its absolute limits, a place where not even light can escape once it crosses a certain boundary. A neutron star, though incredibly dense, remains just on the safe side of that boundary. It has not collapsed completely. Its matter still resists, held up by the pressure of neutrons packed tightly together, but the gravity outside it reveals how close it stands to that final threshold. It is almost a black hole, but not quite, balanced in a narrow zone where extreme conditions exist without the complete surrender that forms a true gravitational abyss. One of the ways this near black hole nature becomes clear is through the escape velocity near the star's surface. Escape velocity is the speed needed to break free from gravity's pull. On Earth, that speed is high but achievable with rockets. Near a neutron star, the escape velocity approaches the speed of light. Only particles moving at extraordinary speeds can break free, and even then only with difficulty. Light, which always moves at its maximum possible speed, barely escapes, losing energy as it rises. Everything else must struggle even harder. This means that the environment near the star is shaped not just by gravity's strength, but by the limitations of what can leave its surface at all. To visualize these extreme conditions, imagine a stretched fabric representing space. A bowling ball placed on that fabric creates a deep curve, and a marble rolling nearby would spiral inward. On Earth, the curve is shallow. Nearby objects roll toward the center but with gentle slopes. A neutron star creates a curve so steep that the fabric seems close to tearing. Marbles dropped near it would not just drift inward. They would race uncontrollably, accelerating with tremendous speed. Even the patterns of the fabric itself would twist, showing how space bends under the pressure of such massive compression. Yet despite these dramatic effects, the region near a neutron star is not chaotic. It is orderly, shaped by predictable physical laws. The strong gravity draws everything inward in smooth paths, guiding particles and radiation along curved routes. Light travels in arcs around a star, bending as it goes. If the star were bright enough, one might see its shape distorted by its own gravity, the light from its far side wrapping around to meet the eye. This effect creates a sense of looking at something both familiar and distorted, like seeing a reflection in curved glass. For grounding, it helps to return to Earth for a moment. The gravity felt every day is the result of Earth's mass pulling everything toward its centre. It is strong enough to keep people grounded, but not so strong that movement is difficult. The air does not flatten. Mountains stand tall. Rivers flow freely. Gravity on Earth is a constant companion, gentle enough to ignore, but powerful enough to shape the planet. Now imagine all of that familiarity replaced by a version of gravity so intense that even the strongest structures would collapse instantly. Any upright object would be flattened. Any movement would be halted. At the surface of a neutron star, gravity becomes the dominant force, overwhelming every other influence. This overwhelming gravitational pull extends far beyond the surface. Objects passing nearby feel the curvature of space, pulled inward along gentle arcs that become steeper and faster the closer they approach. If a spacecraft flew near the neutron star, its path would bend sharply, drawn toward the star with a force far stronger than anything experienced near planets or moons. Even if the craft remained at a safe distance, time on board would tick more slowly, a subtle reminder of the immense mass hidden inside the compact star. The atmosphere, if one can call it that, is thin or non-existent. A neutron star does not hold on to gases the way planets do. The gravity is too strong and the surface too exotic for anything resembling an atmosphere to survive. Instead, the region above the star is filled with magnetic fields, radiation, and particles accelerated by the star's rotation. These elements combine to create an environment that glows faintly in high-energy light, revealing the presence of the star even when its visible light glow is minimal. All of these effects create an environment that feels surreal, almost like stepping into a dream where the rules of motion and perception shift in subtle but profound ways. Space bends, time stretches, light struggles, and gravity pulls with a steady, unwavering force that never relents. This is the landscape surrounding a neutron star, a place where familiar concepts must be reshaped to account for the overwhelming presence of mass compressed into such a tiny space. Yet, for all its extremity, this environment is not unfriendly in a cosmic sense. It is simply the natural result of matter reaching its limit. A neutron star does not pull with malice. It pulls because gravity has been given permission to act at nearly full strength, constrained only by the stubborn resistance of neutrons packed together at unimaginable density. It is a reminder of how flexible the universe's laws can be, how they adapt to conditions ranging from the gentle gravity of Earth to the fierce pull of a nearly collapsed star. In many ways, the gravity near a neutron star tells two stories at once. One story is about extremes, about pressure, mass, and the bending of physics. The other is about balance, about how close the star is to becoming something even more dramatic, and how it remains stable only because the forces within it reach a delicate equilibrium. It is this balance that prevents the neutron star from collapsing further and becoming a black hole. Gravity stands ready to take that final step, but the neutrons resist just enough to keep the star intact. As one imagines drifting near such a star, the feeling is not one of chaos, but of profound calm shaped by overwhelming strength. Space curves smoothly. Time flows gently, even as it slows. Gravity pulls steadily, its presence absolute yet serene. And in this near-silent environment, the neutron star continues to exist in a narrow space between stable matter and total gravitational collapse, a reminder of how strange and beautiful the universe can be when familiar rules meet extraordinary conditions. Magnetic fields near a neutron star behave in ways that feel almost dreamlike, stretching, twisting, and curving with a strength far beyond anything encountered in ordinary life. On Earth, the magnetic field is a quiet companion. It guides compasses, shapes the auroras, and holds a protective bubble around the planet. Its presence is gentle, subtle, and easily taken for granted. But when a star collapses into a neutron star, its magnetic field collapses too, and the effect is extraordinary. What was once a calm, sprawling field becomes compressed into a tiny sphere, concentrating its strength until it reaches levels so intense that ordinary comparisons begin to melt away. During collapse, the star's interior shrinks dramatically. If the star's magnetic field lines were once spread across a sphere the size of a large planetary orbit, by the time the star becomes a neutron star, those same magnetic lines are wrapped around a sphere only a few kilometers in radius. Because magnetic field strength depends heavily on how compact the field becomes, the collapse acts like tightening the coils of a spring. The magnetic fields are drawn closer together, their lines compressed and squeezed until their strength rises to truly staggering levels. To picture this transformation, imagine stretching a rubber band across a wide frame. It sits calmly, with little tension. Now slowly shrink the frame around it. The rubber band begins to tighten, pulling inward, its tension growing with each moment. If the frame keeps shrinking, the tension becomes immense. This is a gentle version of what happens to a star's magnetic field during collapse. The field lines, invisible loops threading through space, tighten dramatically as the star's radius shrinks, storing energy inside twists and folds. The result is a field that can be trillions of times stronger than Earth's magnetic field. At such intensities, magnetic fields stop being simple, passive features of the star. They become active participants in its behavior. They guide charged particles in intricate spiraling paths, forcing electrons and protons to follow the magnetic lines like dancers tracing invisible steps. These particles move with immense speed, emitting radiation as they do so. The beams of radiation produced by these moving particles can sweep outward into space, forming the famous pulsar beams that spin like cosmic lighthouses. The magnetic field also shapes the environment around the star. Close to the surface, it locks charged particles in place, preventing them from drifting freely. Farther out, the field creates loops and arcs that hold particles in suspended motion. In some cases, the field twists so tightly that it stores huge amounts of energy, waiting for the moment when the tension becomes too great. When those tensions snap, sudden bursts of light and energetic particles erupt from the star like magnetic storms releasing their pent-up strength. Among neutron stars, some possess magnetic fields far stronger than the rest. These are magnetars, neutron stars whose magnetic fields are so powerful that they defy easy explanation. If most neutron stars have magnetic fields measured in trillions, magnetars can exceed even that, carrying fields hundreds of times stronger still. The mere presence of such fields alters the behavior of matter around the star. In a magnetar's vicinity, atoms struggle to maintain their structure, stretched into elongated shapes by the overwhelming magnetic pressure. Even empty space behaves differently, as the magnetic field becomes so strong that it affects the vacuum itself. To visualize this magnetic power without overwhelming the mind, imagine ropes made of light, wrapped tightly around the star. These ropes pull and twist, creating tension across the star's surface. The crust beneath them is rigid and strong, but even it can only withstand so much stress. When the magnetic ropes pull too tightly, they can crack the crust, releasing bursts of energy that travel across the cosmos. These bursts are so bright that they can briefly outshine entire galaxies, yet they originate from a crack only a few kilometers across. The relationship between the star's crust and its magnetic field is almost like a quiet conversation. The crust resists while the magnetic field pulls, each influencing the other. When the crust shifts or creaks, the magnetic field responds with subtle changes. When the magnetic tension grows too strong, it pries at the crust, urging it to adjust. This interplay shapes many of the star's behaviors, from the sudden flares of magnetars to the steady pulses of rotating neutron stars. Near the surface, magnetic fields guide particles into narrow paths, funneling them into beams that can stretch across thousands of kilometers. These beams move with the star's rotation, and when they sweep past Earth, astronomers see them as rhythmic flashes of light. The beams are not produced by the star itself, but by particles dancing through its magnetic field, accelerated to incredible speeds and glowing as they move. Further from the star, the magnetic field extends outward in giant looping arcs. These arcs can twist and snap, releasing bursts of energy that ripple through space. The motion of these fields is not random. It follows precise patterns determined by the star's rotation and internal structure. Yet the strength involved gives everything a quiet intensity, as though the magnetic field is constantly humming, vibrating with energy it is unable to release all at once. To understand the scale of these fields, gentle Earth-based comparisons help. On Earth, strong magnets can pick up metal objects or hold notes to a fridge. The planet's own magnetic field protects the atmosphere and shapes the auroras, but the field of a neutron star is so powerful that it could deform the electrons in atoms across vast distances. In the presence of such fields, materials would not behave normally. Metals would twist. Atoms would stretch. Even the vacuum around the star becomes polarized, behaving like a lens made out of empty space. This strength comes from the extreme conditions under which the magnetic field was formed. The collapse of a massive star compresses everything: its matter, its rotation, and its magnetic field. The rapid spin of the neutron star further amplifies the magnetic strength, winding the field lines into tight spirals. In a sense, the neutron star constantly stirs its own magnetic environment, adding energy to the field with every rotation. Thinking of magnetic forces as tension helps keep everything grounded. The magnetic fields behave like tightly wound cords, stretched nearly to their breaking point. These cords tug on the crust, tug on the particles around the star, and even tug on the light passing by. When the cords loosen, they release sudden bursts of energy. When they remain taut, they guide particles with steady precision. This image captures the sense of quiet power that surrounds a neutron star, a power that is always present, always shaping the environment, even when the star appears calm. In magnetars, these cords are wound even tighter. The magnetic pressure is so strong that it holds sway over the entire star. A magnetar flare, when one of these cords snaps, releases energy in a moment that could match what the sun puts out in many thousands of years. These flares happen without warning, yet they come from the same gentle principle: magnetic tension building until the crust can no longer resist. The magnetic fields surrounding neutron stars show that the universe can take familiar concepts and magnify them beyond recognition. A simple magnetic field, something experienced every day on Earth, becomes a force so strong that it reshapes matter, light, and the vacuum itself. Yet through gentle metaphors, ropes tightening, currents flowing, fields humming, the scale can be understood without fear of becoming overwhelmed. Magnetic fields near a neutron star are not just strong, they are transformative. They guide particles, twist space, crack the crust, shape radiation, and influence every aspect of the star's behavior. They provide a quiet, constant reminder that even after the violent collapse of a massive star, the forces it left behind continue to shape the cosmos in ways more powerful and more beautiful than words alone can convey. When a massive star collapses into a neutron star, the transformation is so sudden and dramatic that nothing about the remnant remains slow or gentle. The collapse draws everything inward, shrinking the star from a vast sphere into an object only a few kilometers across, and because the process happens so quickly, the star's rotation tightens with it. Just as an ice skater spins faster by pulling their arms inward, a collapsing star spins faster as its material gathers into a much smaller space. This is why neutron stars often rotate at astonishing speeds, completing many turns every second with a steadiness that feels almost supernatural. The rapid spin sets the stage for something beautiful. Neutron stars have strong magnetic fields, and these fields shape the radiation leaving the star. Instead of shining evenly in all directions, a neutron star emits beams of radiation from its magnetic poles. These beams are incredibly narrow, cutting through space like searchlights. They are not visible in ordinary light, but they appear in radio waves, X-rays, and in some cases even gamma rays. As the star spins, these beams sweep across space in circles, tracing silent arcs that only reveal themselves when they cross the path of a distant observer. If Earth happens to lie within the path of one of these sweeping beams, the neutron star appears to blink. Every time the beam passes over Earth, instruments detect a flash of radiation. It is not a true blink. The star does not dim or brighten, but from far away the effect is remarkably similar. The pulse arrives with clock-like precision, creating a rhythmic pattern that can continue for millions upon millions of years. These are pulsars, the stars that blink not because they choose to, but because their rotation and magnetic fields align in just the right way. The regularity of these pulses is one of their most enchanting qualities. Imagine a lighthouse perched on a cliff, its beams sweeping over dark water at exact intervals. From far away, the lighthouse seems to blink in perfect time, each flash reassuring in its predictability. Pulsars behave the same way. Their beams rotate steadily, completing each turn with the same timing as the last. Some pulsars spin dozens of times per second, while others rotate hundreds of times in that same span. Each rotation sends out a pulse, delivered across great distances with unwavering consistency. This steadiness has made pulsars some of the most reliable objects in the universe. Their pulses arrive with such precision that they can be used like cosmic clocks, Astronomers have used pulsars to measure the motion of stars, the effects of gravity, and even the presence of planets hidden around them. Some pulsars are so regular that if one pulse arrived a fraction of a second late, it would be enough to alert astronomers that something unusual had happened. The timing is that precise. But even the most perfect rhythms slow down eventually. Over long stretches of time, pulsars gradually lose energy. This happens because they are constantly radiating energy outward through their beams. Just as a spinning top slows as it loses momentum, a pulsar slows as it gives away its rotational energy. The change is extremely gradual. It may take millions or billions of years for a pulsar to noticeably slow, but the effect is steady. A pulsar that once completed hundreds of rotations per second may, after enough time, spin only a few dozen, or even a few. The regularity remains, but the tempo changes as the star ages. The slowing of a pulsar is not abrupt or dramatic. It is more like the soft deceleration of a music box winding down. The melody continues, but the rhythm grows quieter and more gentle. In the same way, the beam of a pulsar continues to sweep across space, but the rotation becomes more sedate. Eventually, some pulsars slow so much that their beams become too weak to detect from Earth. They still spin, but their light no longer reaches the instruments that once captured it. To visualize how the beams emerge from the magnetic poles, imagine the neutron star as a spinning globe with two glowing points at its surface. These points send out narrow beams that extend far into space. The beams are fixed in place relative to the star, but the star itself rotates, sweeping the beams around like the hands of a clock. If an observer lies in the path of the beams, they see a flash each time the beam swings by. The pulses repeat with such consistency that they could be used to mark the passing of seconds, minutes, or years with remarkable accuracy. Magnetic fields play a central role in all of this. If the magnetic poles were perfectly aligned with the star's rotational axis, the beams would never sweep past Earth, because they would point in the same direction at all times. But in most neutron stars, the magnetic poles are tilted. This tilt creates the sweeping motion, giving pulsars their rhythmic pulses. The tilt also means the magnetic fields twist and shift as the star rotates, guiding charged particles in complex paths around the star. The particles follow these magnetic lines like dancers tracing intricate steps, sending out radiation as they move. This dance of particles and light gives pulsars their signature appearance. Their beams are incredibly precise, narrow, and focused. They slice through the darkness with a sharpness that makes them easy to detect even from great distances. Some pulsars emit beams so strong that their pulses can be detected across the galaxy. Others emit softer beams, detectable only with sensitive instruments that can pick up faint signals buried in cosmic background noise. The image of a pulsar as a cosmic lighthouse is a gentle and accurate one. It captures the quiet reliability of these stars, their steady rhythm, and their ability to guide astronomers across vast distances. When a pulsar's beam sweeps past Earth, it feels as if a tiny, distant heartbeat has reached across space to announce itself. In a galaxy filled with unpredictable phenomena, pulsars offer a sense of calm regularity. Yet within this regularity lies a subtle hint of change. Although a pulsar behaves like a perfect clock, small variations sometimes occur. A sudden shift in the star's crust, known as a glitch, can cause the pulsar to momentarily speed up. These glitches are rare but revealing. They show that the star's interior is active, that forces deep within the neutron fluid can abruptly transfer momentum to the crust. After a glitch, the the pulsar gradually returns to its slow deceleration, as though resetting itself after a momentary surge. Despite these occasional surprises, the overall behavior of pulsars remains astonishingly consistent. They offer a gentle reminder that even the most extreme objects in the universe can exhibit regular, peaceful patterns. Their beams sweep through the darkness with soft precision, marking time in a way that feels almost comforting. Each pulse is a whisper from a distant star, an echo of its rotation carried across light years. Over millions of years the rhythm slows, the pulses spread farther apart. The star continues its spin but with less urgency. Eventually the pulsar will fall silent, its beams fading into the background of space. But long before that moment arrives, it will have left behind a record of its rotations, a story of its life told through thousands upon thousands of pulses. Pulsars are among the most remarkable remnants of stellar collapse, combining extreme forces with quiet, dependable rhythm. They show that even in the aftermath of some of the universe's most violent events, order can emerge. Their steady pulses move through the cosmos like the heartbeat of a collapsed star, offering a glimpse into a world where time itself is marked by the spin of an object only a few kilometers wide, yet powerful enough to send signals across the void with unwavering consistency. The crust of a neutron star is one of the strongest materials in the universe, a rigid shell forged under pressures so extreme that even diamond would crumble instantly. And yet, despite its astonishing strength, this crust is not unbreakable. Beneath it lies a restless interior of superfluid neutrons and powerful magnetic fields, each pushing and pulling in ways that strain the crust to its limits. Over long stretches of time, those stresses build quietly, like pressure under a frozen lake, until eventually the crust can no longer hold. It cracks, the star shifts, and for a brief moment the neutron star trembles in a deep resonant shudder. This is a star quake, a quiet violence that ripples through one of the densest objects in existence. To imagine a star quake, think of Earth for a moment. Earthquakes happen when the planet's crust shifts along fault lines, releasing stored energy. The ground moves, the air vibrates, and the shaking gradually fades. On a neutron star, something similar occurs, but the forces involved are far beyond anything experienced on Earth. The crust is incredibly rigid, but it rests atop a fluid interior that can rotate at different speeds or drift in ways the crust cannot follow smoothly. This mismatch between the solid shell and the flowing interior creates tension. Over time, the crust strains against these hidden movements until it finally cracks. Magnetic fields also play a role. Neutron stars often possess magnetic fields far stronger than anything found in everyday life. These fields thread through the star like giant taut wires, bending and twisting as the star rotates. As the field shifts, it tugs at the crust, stretching it like a tightly pulled string. If the magnetic tension becomes too great, it can snap the crust suddenly. The star responds with a quake, releasing the built-up strain in a moment of explosive rearrangement. The surface trembles, vibrations ripple inward, and the entire star adjusts itself, settling into a new balance. These starquakes are not gentle events, but they unfold in silence. There is no atmosphere to carry sound, no air to tremble. The vibrations move through solid crust and dense neutron fluid, passing across the star in an instant. The entire neutron star acts like a single unified object, so rigid and compact that a crack in one region can send waves through the whole structure. These waves, deep, powerful oscillations, may last only moments, but they reveal an inner life that would otherwise remain completely hidden. When these quakes occur on ordinary neutron stars, their effects are often subtle. The star's rotation can jump slightly, suddenly spinning a little faster in what astronomers call a glitch. This happens when the fluid interior momentarily couples more tightly to the crust, transferring some of its stored rotational momentum. The result is a cosmic hiccup, a small but measurable shift in the star's behaviour. These glitches act like tiny signposts, letting scientists know that the star's crust has cracked and adjusted itself. But when the neutron star is a magnetar, the story becomes even more dramatic. Magnetars have magnetic fields so intense that they twist the crust constantly, shaping and reshaping the star's outer layers. When a star quake occurs on a magnetar, the release of magnetic tension can trigger a powerful burst of energy. These bursts can shine brighter than entire galaxies for a brief moment. They erupt as sudden flashes of X-rays or gamma rays, racing across space at the speed of light. From far away, these bursts appear as brief, brilliant signals, lasting only fractions of a second but carrying enough energy to be detected across vast stretches of the galaxy. To understand how magnetic pressure causes these bursts, imagine bending a thick wooden branch. As more and more force is applied, the branch begins to creak. Small fractures form, tension builds. When the branch finally breaks, the stored energy is released in a single snap. A magnetar's crust acts much the same way, except the branch is a solid layer of nuclear matter, and the snap sends out a burst of high-energy light, powerful enough to momentarily transform its surroundings. The bursts themselves are short, but the star quake that triggers them is more complex. Beneath the crust, the neutron superfluid moves almost without friction. When the crust cracks, this interior flow shifts, altering how the star rotates and redistributing energy through the entire structure. The vibrations spread like waves in a bell struck with great force. The star rings, not with sound, but with oscillations in its magnetic field, rotation, and interior density. These vibrations gradually fade as the crust and core settle into a new configuration. Starquakes offer a glimpse into the hidden dynamics of neutron stars, revealing how even the strongest materials can reach their breaking point. Yet despite the enormous energies involved, the idea of a starquake can be approached gently. Picture a sleeping creature that stirs in its rest, adjusting its weight, shifting its position, settling back into stillness. A neutron star behaves in a similar way. Its crust cracks not in anger or chaos, but as part of its natural rhythm. The star eases tension that has built slowly over long stretches of time, then returns to its steady rotation with a slight change in pace. Because neutron stars are so dense, the effects of a quake travel with extraordinary speed. A crack forming in one place can send ripples across the entire star in less than a second. This is possible because the crust, though thin compared to the rest of the star, is incredibly stiff. Vibrations move through it at tremendous speeds, carried by the intense density and pressure. Below the crust, the superfluid ocean transmits motion even faster, sending tremors deep into the star's mantle and core. The outcome of a starquake depends on where the stress builds. If the crust shifts near the magnetic poles, the resulting burst can be intense. If the shift occurs near one of the star's rotational bulges, tiny distortions caused by its rapid spin. The glitch in its rotation can be noticeable even across great distances. In either case, the neutron star adjusts itself, letting out a silent, invisible pulse of energy as it settles back into equilibrium. In the calm language of astronomy, a star quake is simply a structural readjustment, but described more softly, it can be seen as the star breathing out tension. It holds immense forces inside: rotation, magnetism, gravity. And these forces do not always align perfectly. Over time, they tug at the crust until a break becomes inevitable. After the quake, the star is still the same object, still spinning, still glowing, still carrying the memory of its collapse. But internally it has shifted just enough to relieve the strain. The idea of a star quake also reveals something gentle about neutron stars. Despite their unimaginable density, their intense gravity and their powerful magnetism, they are not static. They live dynamic internal lives. They move, they adjust, and they shift as needed. Their quakes are part of that behavior, a cosmic version of stretching stiff limbs after a long period of stillness. A magnetar flare, born from a particularly violent starquake, is the universe's way of showing just how much energy these stars can hold. But most quakes are quieter, subtle adjustments that pass unnoticed by anything except the star itself. They leave behind no aftermath, no fire, no shock wave. Only a slight change in rotation, a momentary tremor in the star's structure, and then a return to the steady rhythm that defines neutron stars so well. In these quakes, one finds a balance between calm and force, between silence and power. A neutron star may be one of the most extreme objects in the universe, but its quakes reveal a kind of delicate ongoing negotiation within its interior. The crust cracks, the star vibrates, the stresses ease, and the rhythm continues. It is a reminder that even in the deepest extremes of physics, there is room for cycles, adjustments, and quiet, resonant change. A newborn neutron star begins its life in a state of almost indescribable heat. Moments after the supernova explosion ejects the outer layers of the original star, the collapsed core that remains is still glowing with the temperature of its former self. The heat locked inside it is so intense that the surface can reach levels far beyond anything the sun has ever achieved. It shines not with gentle warmth, but with the fierce energy of matter compressed and shaken by collapse. In these first seconds and minutes, the neutron star is one of the hottest objects in the universe. This heat comes from the violent restructuring of matter. When the star collapsed, atoms were crushed into neutrons, protons were forced to merge, and particles were rearranged under enormous pressure. Each of those changes released vast amounts of energy, and that energy lingers inside the newborn neutron star like the afterglow of a cosmic furnace. For a moment the surface radiates with astonishing brightness, and the interior glows with heat that has not yet had time to escape. But something remarkable begins almost immediately. The star cools. Not slowly at first, but rapidly, almost breathlessly. Within minutes the temperature begins to drop. Within hours it has fallen dramatically. And within days the neutron star is far cooler than it was at birth, though still extraordinarily hot by any earthly measure. The reason for this swift cooling lies not in the star's surface, but deep inside it, where particles known as neutrinos carry energy away. Neutrinos are the universe's quietest messengers. They interact so weakly with matter that trillions of them pass through every person every second without leaving a trace. Inside a newborn neutron star, they are produced in staggering quantities. As neutrons settle into their new arrangement and reactions occur within the dense core, neutrinos are released in a steady stream. They escape almost effortlessly, carrying heat away into space. Their ability to slip through dense matter makes them extraordinary cooling agents, capable of draining energy from the star faster than radiation ever could. For the first several years, neutrinos dominate the cooling process. The young neutron star loses temperature at an astonishing rate, leaving behind a core that grows steadily more stable. The surface cools more slowly, taking time to reflect the rapid changes happening within. If someone could watch a neutron star across its first decade of life, they would see a transformation more dramatic than almost anything else in the universe. A blazing, newborn object fading into a still hot but calmer remnant. After these early years, the cooling slows. The easy energy has been carried away. Neutrino production begins to decline, and the processes that once drained the interior quieten. The neutron star enters a long, tranquil period where heat must escape through slower means. Radiation now takes over, and the star cools through a steady release of light and thermal energy from its surface. This phase lasts for millions of years, a gentle descent into deeper and deeper calm. During this time, the star's outer layers gradually cool enough that the crust becomes more rigid. The heat from the interior continues to rise through the layers, warming them as it passes. Even as the neutron star grows older, its interior remains remarkably warm, insulated by its incredibly dense structure. Heat moves slowly through such compact material, and the star's cooling journey stretches across the ages in a way that mirrors the slow changes of mountains or continents on Earth. Nothing happens quickly. Everything unfolds at a pace measured in cosmic time. As the star ages into hundreds of thousands of years, the surface temperature continues to fall. It no longer glows in visible light, and only faint traces of heat can be detected. But deep inside, the temperature remains high. This is because the density of the star traps heat. The particles inside are so tightly packed that they can share energy for millions of years before the star can release it. Even very old neutron stars, ones that have existed longer than early human ancestors, still retain warmth within their cores. This lingering warmth is comforting in a way. It shows that a neutron star's journey is not a sudden fall from heat to cold, but a long, slow cooling that stretches across eons. The star retains its inner heat the way a stone holds warmth after a summer day, but on a timescale that dwarfs everything familiar. A neutron star cooling is not like water losing heat, or metal cooling in the air. It is more like watching the warmth of a mountain fade over ages, a process so slow and steady that it becomes a story of patience rather than change. Cooling also depends on the star's composition. Some neutron stars cool faster if their cores contain more exotic forms of matter, such as particles that allow efficient neutrino emission deep inside. Others cool more slowly if the interior settles into stable arrangements that resist energy loss. Even the star's magnetic field can influence how heat escapes through the crust. Each neutron star follows its own cooling path, shaped by its initial mass, its rotation, and the details of its collapse. Yet despite these variations, the overall cooling story remains one of gradual decline. The early fire fades quickly. The long cooling follows like a peaceful exhale, turning the neutron star into a quiet, dim remnant. Even after millions of years, the star is not frozen. Its interior still hums with residual heat, and the crust still carries traces of energy from the star's youth. Over even longer timescales, stretching into billions of years, the star continues to cool until it becomes almost completely dark, a hidden ember drifting through the universe. If one were to imagine touching such a star, the surface might feel cool, at least compared to its past, but beneath that crust would lie layers that still glow with warmth. It takes extraordinary time for that heat to fade, because nature has placed the heat inside a container that resists change. A neutron star's cooling is the epitome of cosmic patience. To gently compare this cooling to earthly experiences, imagine a metal sphere heated until it glows. Remove it from the fire and the surface cools first. After a while, the heat deep inside slowly moves outward. This sphere remains warm long after the surface stops shining. A neutron star behaves similarly, but the timescales stretch beyond imagination. Instead of hours, the deep warmth persists for millions upon millions of years. These immense spans of time offer a reminder of how slowly the universe moves on its own schedule. Stars can collapse in fractions of a second, but the cooling afterward is unhurried and calm. A neutron star's heat traces a path from the intensity of a fresh collapse to the quiet glow of an ancient remnant. In that slow journey, there is a gentle rhythm, the kind that encourages reflection on the vastness of time. Old neutron stars, even when they no longer pulse brightly or shine in visible light, carry the memory of their beginning in the warmth still trapped deep inside. They drift through space as quiet survivors, their heat fading inch by inch, century by century. Their cooling is not a race, but a story of endurance, shaped by the physics of dense matter and the passage of cosmic ages. In this long cooling process lies the quiet poetry of neutron stars. They begin in fire and collapse, burn fiercely through neutrino release, then drift into slow, silent cooling that unfolds across eons. They are reminders that even the most violent events in the universe can give rise to long periods of calm, where heat fades gently and time stretches into something wide, soft, and serene. Some neutron stars spend their long lives alone, drifting quietly through space with only their internal rhythms for company. Others, however, remain bound to a partner. These neutron stars live in binary systems, locked in a gravitational embrace with another star. Their orbits may be wide or tight, calm or dynamic, but in every case the two objects move around a shared centre of gravity, engaged in a cosmic dance that can last for millions or even billions of years. The companion can take many forms. Sometimes it is a star very much like the one that originally collapsed to form the neutron star. Sometimes it is a smaller, cooler star, glowing softly in the darkness. In rare cases, the companion might be a white dwarf, or even another neutron star. Regardless of its nature, the companion star and the neutron star influence each other in ways both gentle and profound. Their mutual gravity shapes their orbits, drawing them into paths that repeat with steady rhythm. From a distance, this orbit might appear serene, like two dancers circling one another in perfect balance. But up close, the situation can be much more dramatic. If the companion star drifts too close, or if its outer layers expand as it ages, material can spill outward, forming a stream of gas that flows toward the neutron star. Gravity becomes the guiding hand, pulling this gas inward, shaping it into a swirling disk around the neutron star. This process, known as accretion, is one of the most revealing behaviors in binary systems. Accretion disks form when matter spirals slowly toward the neutron star, moving in graceful, tightening circles. As the gas nears the star, its speed increases. Friction and compression within the disk heat the gas until it glows with tremendous energy. This glow is not visible to human eyes, but it shines fiercely in X-rays. making many accreting neutron stars some of the brightest X-ray sources in the sky. These X-rays tell a story of matter drawn into an intense gravitational field, heated until it emits light that cuts through space like a whisper from the star's surface. When the infalling gas finally reaches the neutron star, the energy release becomes extraordinary. The gas crashes onto the surface at immense speeds, heating small regions of the crust and creating bursts or flickers of X-ray light. These flickers repeat with the neutron star's rotation, revealing its spin, magnetic field, and the structure of its surface. The rhythm of these flashes can show how matter behaves under extreme pressure and gravity, offering glimpses into the physics deep inside the star. In some systems, the neutron star's magnetic field channels the accreting material into narrow streams that fall onto the magnetic poles. As these streams hit the surface, they create bright, concentrated hotspots that pulse with clock-like regularity. The result is an X-ray pulsar, a neutron star whose pulses are shaped not by its rotating beams of radiation, but by its magnetic manipulation of falling gas. The pulses provide astronomers with the tool to measure the star's rotation, its magnetic geometry, and the rate at which it gathers material from its companion. Through these systems, neutron stars reveal their internal secrets. The timing of pulses shows how rigid the crust is. The energy of bursts reveals how heat travels through the outer layers. The way the star interacts with the disk exposes how its magnetic fields reach into space, and the gradual changes in rotation offer clues about how superfluid matter moves beneath the crust. Binary systems act as natural laboratories, allowing scientists to study conditions that no experiment on Earth can reproduce. The process of accretion can be gentle or intense. Sometimes the flow of matter is steady, forming a stable disk that shines softly in X-rays. Other times the flow becomes unstable, with bursts of material falling inward in pulses. These bursts can cause sudden brightening, transforming the neutron star from a faint object into a dazzling source of high-energy light. The variations in brightness offer further clues about the behavior of matter under extreme pressure and temperature. The orbital dance itself is worth appreciating. Two stars move around a shared point, pulled by gravity yet never touching. Their motion is smooth and predictable, like two carefully paired performers tracing arcs across a dark stage. The neutron star, small and dense, exerts a powerful pull. The companion star, larger and more diffuse, responds by shifting its outer layers toward the neutron star's gravitational influence. The result is a delicate exchange of motion and matter, controlled by forces that act across millions of kilometers. Sometimes the binary system evolves in unexpected ways. If the companion star loses too much mass, its orbit may change, drawing it closer to the neutron star or pushing it farther away. If the neutron star gathers enough material, its rotation may speed up dramatically, turning it into a millisecond pulsar, an object that spins hundreds of times per second. These millisecond pulsars are among the most precise natural clocks ever discovered. Their rapid rotations smoothed by long periods of steady accretion. In rare and dramatic cases, two neutron stars orbit each other. Over millions of years, their orbits shrink as they lose energy through gravitational waves, ripples that carry away tiny amounts of momentum into space. Eventually, the neutron stars draw close enough to collide. Such collisions produce bursts of gravitational waves and light, creating heavy elements like gold and platinum in the process. These events are rare and violent, yet they begin with the same gentle orbital motion that characterizes all binary systems. To understand the gentler, everyday behavior of neutron stars in binary pairs, it helps to imagine a duet between two objects with very different personalities. The companion star is warm and diffuse, stretching its outer layers into space. The neutron star is dense and compact, pulling quietly but firmly. Their relationship is shaped by distance, rotation, and the flow of matter between them. Each orbit is a step in their dance, a repetition of a motion that can last for ages. Accretion itself can be thought of as a soft, continuous offering from one star to another. Matter drifts across space, forming spirals that gather around the neutron star. These spirals tighten and glow, each rotation bringing the gas closer until the neutron star absorbs it. The glow of X-rays is the signature of this exchange, the light produced when matter meets one of the densest surfaces in the universe. Binary systems also show that neutron stars are not only remnants of catastrophic events, they can be part of living, ongoing processes. Their interactions with companion stars reveal new aspects of their behavior, adding depth to the story that begins with their formation. Through accretion, pulses, bursts, and orbital motion, neutron stars in binaries continue to evolve long after their birth. In the calm light of metaphor, these systems resemble partnerships shaped by gravity instead of emotion, by mass instead of intention. They move together because the cosmos has bound them in orbit, sharing energy and motion over long stretches of time. Their interactions are quiet but powerful, offering astronomers insights into some of the universe's most extreme conditions. A neutron star in a binary system may shine brightly in X-rays, pulse rhythmically, or quietly gather material from its companion. But beneath all these behaviors lies a single theme: the gentle, persistent influence of gravity linking two stars in a shared journey. Their orbit may be slow or swift, stable or shifting, but it remains a testament to the enduring connections that gravity can weave across the dark expanse of space. Two neutron stars circling one another form one of the quietest and most powerful partnerships in the universe. From a great distance, their motion appears serene, almost like two stones drifting in a slow current. They orbit calmly at first, tracing predictable paths around a shared centre of gravity. Yet beneath this calm motion lies an invisible loss of energy. With every orbit, the pair releases tiny ripples in space-time, known as gravitational waves. These waves carry energy away little by little, so gently that the stars barely notice. Across millions of years, the effect accumulates. Their orbit shrinks, their pace increases, their quiet dance begins to tighten. As the stars draw closer, their motion becomes more rapid. The once wide arcs of their orbit narrow into spirals. They move faster, pulled by a gravitational attraction that strengthens with every passing moment. Even though they are tiny on cosmic scales, their density makes them enormously influential. Their gravitational pull is fierce, knitting their orbits together in a pattern that grows more intricate as the distance between them decreases. Yet despite this rising tension, the movement remains smooth. There is no sudden jolt or violent shift in these early stages. The stars simply continue to circle, bound by gravity's steady guidance. The entire process feels like a slow tightening of a cosmic waltz, each step drawing them closer, each turn carrying them deeper into a shared fate. Eventually the final moments arrive. The neutron stars reach a point where they can no longer orbit peacefully. Their distance shrinks to just a few kilometers, and the speed of their rotation becomes astonishing. They complete hundreds of orbits in a single second, whirling so quickly that space-time ripples outward in powerful bursts. The stars elongate slightly as tidal forces grip them, stretching their dense matter like taffy made of neutrons. Yet even now the motion remains strangely graceful. When the collision finally occurs, it is both violent and beautiful. The two neutron stars merge in a moment of unimaginable density, releasing a flood of energy that washes through their surroundings. This explosion is called a kilonova, a transient light show so radiant that, for a brief time, it can outshine an entire galaxy. But unlike a supernova, whose brilliance comes from light thrown off by an imploding star, a kilonova shines because matter itself is being reshaped. At the moment of impact, enormous amounts of neutron-rich material are flung outward. This matter is unlike anything found on Earth. It is super dense, neutron-filled, and unstable in its raw form. As it expands and cools, the neutrons begin to bind with protons, forming the heaviest elements in the periodic table. Gold, platinum, uranium, and other rare elements are assembled in these fleeting, chaotic seconds. The universe uses the collision of neutron stars as a forge, crafting the materials that later become jewelry, technology, and the building blocks of planets. To imagine this process more gently, picture a quiet workshop lit by a single lamp. In the centre sits a craftsman shaping precious metals with careful, deliberate movements. A neutron-star collision is like the universe's version of that workshop, except the scale is vast and the materials are born in fire rather than moulded by hand. The heavy elements that form in these events drift outward into space, eventually cooling, mixing with gas and dust and becoming part of future generations of stars and planets. The light of the kilonova fades quickly. What lasts much longer is the scattering of matter that follows. The newly formed elements drift through space like glowing embers, carried on cosmic winds. Over time, they join interstellar clouds, merging with other materials, waiting to form something new. Every piece of gold that exists today, every ring, every coin, every trace embedded within Earth, was once created in a moment like this. The beauty of these elements lies not only in their rarity but in their origin, a collision so dense and bright that it reshaped matter at its core. Inside the merging stars, the physics becomes even more extreme. The remnants of the two neutron stars may briefly form a larger, hypermassive neutron star, one that exists only for moments before collapsing under its own weight. In other cases, the merge leads directly to the formation of a black hole, a region where gravity becomes so strong that nothing, not even light, can escape. But whether the final result is a larger neutron star or a black hole, the collision always leaves behind the same signature: gravitational waves rippling outward and heavy elements scattered across space. These gravitational waves are subtle yet revealing. They pass through the universe, stretching and compressing space-time ever so slightly. Instruments on Earth can detect these waves, capturing the final echoes of the star's dance. The pattern of those waves tells scientists about the composition, mass and structure of the stars just moments before they merged. In this way, even the most violent moments in the collision become sources of information, allowing astronomers to peer into the behavior of matter under pressures impossible to recreate in a laboratory. Despite the intensity of neutron-star collisions, there is a quietness to the story they tell. The stars spend most of their lives in slow orbits, spiraling inward with patience shaped by gravity. The kilonova itself, though brilliant, is brief, and the elements created during the explosion drift through space silently, beginning journeys that may take billions of years before they become part of a planet or a living being. The violence exists, but it is wrapped in long stretches of calm, like thunder following a distant lightning flash. It is soothing in a way to think that something as familiar as gold comes from an event so rare and powerful. The atoms that form the metal in a ring or necklace began their existence in a moment of cosmic transformation. Two stars, each only a few kilometers wide, collided in a distant corner of the galaxy, and in that brief instant produced the elements that would one day settle into a new world. Even after the collision ends, the remnants continue their story. If a black hole forms, it sits at the center of the expanding debris, watching silently as the material drifts outward. If a larger neutron star remains, it may spin rapidly, throwing off radiation as it stabilizes. In either case, the story that began with a spiral ends in a kind of quiet release, as the universe absorbs the energy, light, and matter of the event. And yet, for all the intricacy and intensity of neutron-star mergers, their ultimate message is simple. They show that creation and destruction are often intertwined. Heavy elements are born from collisions, light bursts from violence, and long-lasting beauty emerges from moments of cosmic upheaval. A neutron-star merger is one of the universe's grandest acts of transformation, turning dense stars into the raw materials for future worlds. In their spiraling approach, in their collision, and in the soft glow of their aftermath, neutron stars remind us that even the most extreme events can lead to gentle, enduring outcomes. Gold resting quietly in a vault or adorning a hand began its life in a fire that lit a galaxy. Platinum in electronics came from the heart of a neutron star. The universe reshapes itself through these events, weaving new materials into its endless tapestry. The dance of two neutron stars is slow, the collision brief, and the legacy eternal. It is a story of motion, pressure, light, and transformation. A reminder that even in the deepest corners of space, creation often begins with a quiet, spiraling embrace. When two neutron stars spiral toward one another, their motion does more than draw them into an eventual collision. Long before the final moment, their orbit stirs the fabric of space-time itself. Every turn, every tightening loop, every shift in their path sends out a subtle disturbance that travels across the universe. These disturbances are gravitational waves, gentle ripples moving through space-time the way small waves move across the surface of a still pond. To imagine this more clearly, picture a calm lake at dawn. The water is perfectly smooth. Then a single pebble drops into the center. Circles spread outward, growing wider and fainter as they move across the lake. Gravitational waves behave in much the same way, except the lake is the fabric of space-time, and the pebble is the motion of massive objects. When neutron stars orbit, they disturb the calm surface. When they collide, the pebble becomes a boulder, and the ripples race outward with renewed strength. Because neutron stars are so dense, their spiraling motion creates some of the strongest gravitational waves the universe can produce. The waves begin softly during the early stages of orbit, when the stars circle far apart. These early ripples are faint, so gentle that they pass through galaxies without leaving a mark. But as the orbit shrinks, the ripples grow slightly stronger. In the final seconds before impact, the waves become rapid, each cycle growing shorter and more urgent until the collision produces a final burst of ripples that spread outward in every direction. What makes gravitational waves so extraordinary is their subtlety. They stretch and squeeze space-time by unimaginable small amounts, far smaller than the width of an atom. Everything in their path is gently elongated, then gently compressed, all without producing sound or light. They do not disturb matter the way other waves do. They pass through planets, stars, dust, and gas without resistance. A gravitational wave moving through a galaxy barely slows down. It simply continues on its path, carrying with it the memory of the motion that created it. For most of human history, such waves remained purely theoretical. They were predicted long before they were observed, based on the idea that massive objects moving in curved paths must radiate energy in a unique and subtle form. The challenge was detecting them. How can one measure a wave that changes length by less than a fraction of a fraction of a fraction of a single proton? How does one observe a ripple that leaves everything practically unchanged? The answer came from building instruments sensitive enough to notice these impossibly tiny shifts. One of the most famous is LIGO, an observatory that uses long tunnels filled with laser light to measure minuscule changes in distance. These tunnels stretch for kilometers in straight lines, arranged like the arms of a giant letter L. When a gravitational wave passes through Earth, it stretches one arm slightly and compresses the other, then reverses the effect as the wave continues onward. The laser light inside the tunnels can detect these differences, revealing the quiet passage of a ripple from across the universe. The first time LIGO detected a gravitational wave, it was like hearing a sound that had never been heard before. A faint chirp, a soft upward sweep of frequency, marking the final orbits and collision of two massive objects. That detection showed not only that gravitational waves exist, but that neutron stars and black holes can be observed through their motion, even when no light escapes from the event. When LIGO later detected the gravitational waves from merging neutron stars, it opened a new chapter in astronomy. For the first time, scientists could listen to the universe in a way that did not rely on light. The collision produced a unique signature that told a story of mass, spin, and orbit. It revealed how close the stars were just before merging, how quickly they moved, and how much energy they released. The gravitational waves were followed by a flash of light detected by telescopes, confirming that the merger had produced a kilonova. This combination of observations, listening and seeing, allowed scientists to piece together the entire event from beginning to end. Gravitational waves carry information that light cannot. They are unaffected by dust or gas. They cannot be blocked or scattered. They carry details about the internal structure of neutron stars, because their shape and stiffness influence the pattern of ripples produced. When two neutron stars deform each other during their final orbits, those deformations leave fingerprints in the gravitational waves. The shape of the wave tells scientists whether the stars were soft or rigid, whether their matter was easily compressed or strongly resistant. These clues help reveal what happens inside a neutron star's core, a place where matter reaches densities no experiment can imitate. The elegance of gravitational waves lies in their simplicity. They do not roar or crackle. They do not shine or pulse. They glide silently, stretching space-time without resistance. Even when produced by catastrophic events, they are gentle by the time they reach Earth. They arrive as faint echoes, tiny nudges in the fabric of reality, hardly noticeable yet carrying immense significance. It can be soothing to think of these waves passing through everything, including human bodies, Earth's mountains and the deepest oceans, without causing harm. Every so often, a gravitational wave washes across the planet, leaving behind a subtle change that no one feels. It is like being brushed by the shadow of a travelling cloud, present but soft, fleeting yet meaningful. What makes these ripples important is not their strength, but their message. They tell of stars spiraling toward one another over millions of years. They reveal the moment of impact when two dense bodies merge into one. They bring news from distant galaxies where such collisions occur quietly in the vastness of space. They show that gravity is not just a force pulling things downward, but a dynamic, shifting part of the universe that can ripple and flow like water. Observing gravitational waves has transformed our understanding of the cosmos. It allows astronomers to map invisible systems, track the lives of compact stars, and watch the formation of black holes. It adds a new sense to astronomy, not just seeing the universe, but listening to it. The universe becomes a place filled with gentle murmurs and distant tremors, all carried by waves that stretch through space and time. Even the soft hum of Earth itself can glow with gravitational waves. If one could tune into them naturally, it would be like hearing a faint cosmic choir, each note produced by massive objects moving in ways too distant to see. Gravitational wave observatories act as ears tuned to that quiet music, capturing each ripple and turning it into a story humans can understand. In this way, gravitational waves embody both power and peace. They come from collisions, explosions, and spiraling stars, yet they travel with a calm grace. They show that even the most extreme cosmic events can leave behind something delicate. A wave so faint that it moves through entire galaxies without leaving a trace, yet meaningful enough to change how the universe is understood. They remind us that the universe communicates in many ways. Some messages are written in light, others in particles, and some in ripples that pass silently through everything. The more humans learn to recognize these signals, the more complete the cosmic story becomes. The invisible motions of neutron stars, once hidden forever, now create quiet waves that gently reach Earth, carrying news of distant dances and celestial mergers across the wide, breathing fabric of space-time. Studying neutron stars begins with a simple truth. These objects are far too distant, far too small, and far too dense for anyone to approach directly. Everything known about them comes from light, particles, and ripples that travel across incredible distances before reaching Earth. This limitation might seem restrictive, yet it has encouraged astronomers to develop an entire suite of tools built on patience, creativity, and quiet observation. Each method offers a different window into these compact stars, and together they form a gentle, detailed portrait of some of the most extreme environments in the universe. One of the most important tools is the family of telescopes that observe neutron stars across many wavelengths of light. Each wavelength reveals something different, much like watching a landscape change under morning sunlight, midday brightness, and evening glow. Radio telescopes pick up the rhythmic pulses from spinning neutron stars, mapping their rotations and measuring their stability. X-ray telescopes reveal hotspots and bursts, showing where matter falls onto the star or where the crust cracks. Gamma-ray telescopes observe the brief, powerful flashes produced by magnetar flares. Even optical telescopes, though less commonly used for neutron stars, can sometimes catch faint glimmers from especially bright or nearby systems. Each wavelength brings a new layer of understanding. Radio waves stretch across vast distances with ease, carrying the clear, steady beat of pulsars. X-rays, high in energy, expose the behavior of accreting neutron stars, those that gather material from nearby companions. Gamma rays highlight the most dramatic moments, when magnetic tensions snap or a magnetar releases a burst. Every part of the electromagnetic spectrum offers its own insight, and together they allow scientists to build a long, calm picture of how neutron stars behave. For pulsars in particular, timing arrays are among the most valuable tools astronomers use. A pulsar timing array is not a single instrument, but a network of radio telescopes spread across Earth, all listening to the regular flashes of dozens of pulsars at once. These telescopes track the timing of each pulse with remarkable accuracy, noting tiny deviations in arrival time. If a pulse arrives later or earlier than expected, that small shift can reveal something happening either within the pulsar itself or in the space between the pulsar and Earth. The beauty of pulsar timing arrays is their precision. Pulsars rotate so steadily that their pulses can be predicted with astonishing accuracy. When something changes, even slightly, astronomers can trace the cause. These changes might come from star quakes, where the crust shifts and the rotation adjusts. Sometimes they come from small planets orbiting the pulsar, tugging it gently. And sometimes they reflect ripples in space-time passing between Earth and the pulsar, providing hints of gravitational waves on enormous scales. In this way, timing arrays turn the galaxy into a natural laboratory, using the stars themselves as instruments. Gravitational wave observatories add another dimension to the study of neutron stars. While ordinary telescopes watch light, observatories like LIGO and Virgo listen to space-time. Their long arms detect tiny stretches and squeezes as gravitational waves pass through Earth. These waves provide information light cannot. When two neutron stars spiral together and merge, the gravitational waves reveal their masses, spins, and the structure of their interiors. The exact shape of the wave contains subtle details about how rigid or soft the matter inside each neutron star was just before collision. Light can show the explosion that follows, but gravitational waves capture the approach, the embrace, and the final merging. These observatories require tremendous sensitivity. They measure changes smaller than a fraction of a proton's width. Yet those small changes carry the signature of events that happened millions or even billions of years ago. The quietness of the signal contrasts with the violence of the source, creating a peaceful connection between observers on Earth and the distant remnants of collapsed stars. Because no single method can tell the whole story, modern astronomy relies on a technique called multi-messenger observation. This approach combines data from telescopes, timing arrays, neutrino detectors, and gravitational wave observatories, weaving them together into a coherent understanding. When a neutron star merger is detected, scientists look for its electromagnetic glow, its gravitational wave signature, and any particles that might accompany it. When a magnetar bursts, observers check gamma-ray telescopes and radio instruments for matching behavior. By using many channels at once, astronomers can see not only what happened, but how it unfolded and how the different pieces of the event connect. This collaboration extends across continents. Different observatories share data, coordinate observations, and check their findings against one another. The process is slow, careful, and methodical. A detection may last only a second, but analysing it can take months of quiet effort. Data must be compared, noise removed, and patterns confirmed. The patient nature of this work mirrors the patience of the universe itself, where neutron stars can spin for billions of years, and collisions can take millions of years to unfold. Even the simplest details of neutron star science come from careful observation. The distance to a neutron star can be estimated from how its pulses scatter through interstellar gas. The surface temperature can be inferred from the spectrum of its X-ray glow. The strength of its magnetic field can be measured from how it spins down over time. Each piece of information requires subtle interpretation, like listening to the softest notes in a piece of music and understanding how they fit the whole melody. Some neutron stars are so distant or faint that they can only be studied indirectly. Their presence may be inferred from how they pull on nearby stars, or from faint signals hidden in a larger data set. Others reveal themselves through sudden bursts, giving scientists a brief moment to gather as much information as possible before the star falls silent again. These brief episodes can be unpredictable, yet when they occur, observatories around the world turn their attention toward them, recognizing that even a single burst can offer valuable insights. A significant part of neutron star research also happens through computer modeling. Scientists take observational data and use it to simulate the behavior of matter at high densities, the movement of magnetic fields, and the formation of accretion disks. These simulations help fill in gaps between what telescopes can see and what actually happens deep inside the star. They allow researchers to test different theories gently, adjusting parameters until the model matches reality. This interplay between observation and simulation forms a quiet dialogue between what is seen and what is imagined. The study of neutron stars requires patience, not unlike tending a slow-growing plant or watching a long tide rise and fall. Some neutron stars reveal their secrets quickly, flashing brightly or pulsing with intense regularity. Others require decades of observation, their timing patterns changing subtly over years. Scientists build long timelines for these stars, gathering data that stretches back through generations of instruments. There is a humble beauty in this kind of work. Neutron stars are powerful, exotic, and extreme, yet the methods used to study them rely on steady attention and gentle interpretation. Observers do not rush. They wait for pulses to arrive, for waves to pass, for bursts to glow. They collect signals faint enough to be lost in the noise, trusting that careful analysis will bring meaning forward. Studying neutron stars from afar becomes a quiet partnership between humanity and the cosmos. The stars send out their pulses, waves, and bursts without intention, and Earth listens. Telescopes align, arrays connect, observatories strain to detect faint distortions. In their own way, these tools mirror the neutron stars they study, steady, precise, patient. And through this persistent attention, the universe opens itself a little more, allowing its deepest mysteries to be understood with calm curiosity and respectful wonder. The periodic table may look tidy and orderly, a simple grid of elements arranged by number and behavior, but its true story is far broader and older than anything written on a chart. Each element carries within it a history shaped by stars, collisions, and the quiet unfolding of cosmic time. Hydrogen, the simplest element, was born in the first minutes after the universe began. Helium followed soon after. But almost everything else in the periodic table comes from stars, from explosions, and from the rare and powerful merging of neutron stars. The matter that surrounds you, and the matter you are made from, carries the imprint of these events. For most of the universe's history, stars have acted as factories for elements. Deep in their cores, fusion gradually builds heavier nuclei. Lighter elements merge to form heavier ones, a process that shapes the middle of the periodic table. Carbon, oxygen, silicon, and many metals form in these stellar furnaces. When massive stars run out of fuel and collapse, their outer layers explode, scattering these elements across the galaxy. The explosion enriches space with material that will later become planets, moons, and the building blocks of life. Yet this stellar process can only go so far. Fusion stops once the elements reach iron. Creating anything heavier than iron requires energy rather than releasing it, and stars cannot supply that energy through ordinary fusion. Something far more extreme is needed to push matter across that boundary. This is where neutron stars enter the story. Their collisions offer the perfect combination of density, pressure, and neutron-rich matter to form the heaviest elements in the periodic table. When two neutron stars merge, their collision sends vast amounts of neutron-rich debris into space. This debris expands and cools, allowing neutrons to combine with protons in a cascade of reactions. Gold, platinum, uranium, and many other rare elements take shape in those few seconds of transformation. The universe produces these elements in no other significant way. They are not made in the hearts of stars nor in supernovae to any meaningful degree. They are created in the brief, brilliant light of a kilonova, a moment when two collapsed stars lose their separate identities and create something entirely new. The heavy elements born in these collisions drift outward, mixing with surrounding gas and dust. Over millions of years, these enriched clouds collapse under gravity to form new stars and planets. Within these planets, the heavy elements become part of mountains, oceans, soil, and the metals that civilization depends on. Every gold ring, every platinum contact in electronics, every grain of radioactive material buried deep underground owes its existence to a neutron-star merger that happened somewhere in the distant past. This connection stretches all the way from the violent hearts of merging neutron stars to the small, everyday objects resting quietly in your home. The metal in a wedding band may trace back to a collision billions of years ago, long before the Earth formed. The elements in a computer circuit began as dust drifting through interstellar clouds. Even the elements in soil, though formed by many different processes, are shaped by mixtures of materials seeded across the galaxy from ancient stellar events. In a gentle way, reflecting on this connection can shift the way one views the familiar. The objects around you are not merely products of factories or craftsmen. They carry the memory of cosmic events. Their atoms have travelled through space, waited in clouds of dust, and passed through stages of formation that spanned unimaginable stretches of time. It is a quiet reminder that the boundary between the cosmic and the everyday is far thinner than it seems. This story extends even further inward, into the human body itself. Many of the elements essential for life, carbon, oxygen, nitrogen, phosphorus, were formed in stars that lived long before the sun. The iron in your blood came from the collapse of stars that exploded before the Earth existed. The calcium in your bones, the sodium in your nerves, the magnesium aiding your cells. All of these elements have stellar origins. Most of them were formed in the fiery cores of massive stars, later scattered by supernovae into the interstellar medium from which the solar system emerged. But not all the elements in the human body come from stars alone. Tiny traces of heavier elements, present in minute quantities, carry the legacy of neutron-star collisions. Though they make up only a small fraction of the matter you contain, their presence ties the human body to the most extreme events in the universe. The gold used in medical tools, the iodine used for health, and even the rare elements that move through ecosystems owe their existence to these mergers. This connection is not meant to be sentimental, only factual and quietly profound. It places humanity within the broader narrative of the cosmos. Human bodies are made from materials shaped by stars. The Earth is built from the remnants of celestial collisions. Even the tools made by human hands rely on elements forged in ancient events that unfolded far from the solar system. It is a reminder that the universe is not a distant backdrop, but a place where everything is connected through matter and time. Even the distribution of elements across the periodic table tells a story. The abundance of lighter elements reflects their creation in the early universe and the interiors of stars. The relative scarcity of heavy elements mirrors how rare neutron-star collisions are. Gold is precious not because of its gleam, but because the process that creates it happens infrequently and violently. Platinum's rarity has nothing to do with difficulty of extraction on Earth, and everything to do with the tiny number of kilonovae across the galaxy's long history. As neutron stars continue to merge in distant corners of the universe, they enrich the galaxy in slow, gentle steps. The process is not hurried. It unfolds across eons. Each collision sends out one more cloud of heavy elements. These clouds drift through space, slowly becoming part of new star systems. Over billions of years, this gradual accumulation shapes the chemical richness of galaxies. It determines which worlds can form complex structures, which can host oceans, and which can develop atmospheres rich in diverse elements. This long, patient process mirrors the quiet, steady behavior of neutron stars themselves. Their collisions are rare, but their contributions are lasting. They shape the materials that define worlds, mountains, technologies, and even living bodies. When viewed on human timescales, the process seems almost invisible, but on cosmic timescales, it becomes one of the universe's most significant sources of transformation. Reflecting on this can bring a sense of calm perspective. The world is filled with reminders of cosmic history, not dramatic or obvious ones, but small, everyday signs. A piece of jewellery containing gold is a physical relic of a stellar merger. A trace of rare elements in soil hints at distant explosions and ancient collisions. The iron that carries oxygen through your bloodstream once flowed through the heart of a star. The carbon that forms the backbone of life was shaped in nuclear reactions long before Earth existed. This story is not mystical. It is simply the quiet truth of how the universe forms and distributes matter. The periodic table is not just a scientific chart. It is a map of cosmic processes, each element pointing to an event. A star's life, a collapse, a merger, or a moment of nuclear assembly in the early universe. Learning this can transform the way one sees everyday materials, inviting a gentle awareness of the history contained in even the smallest atoms. Neutron stars, in their rare collisions, perform one of the universe's most meaningful acts of creation. They take matter compressed to unimaginable densities and release it into space, where it becomes part of something larger. They contribute to the richness of galaxies, the diversity of planets, and the ingredients necessary for life. Through this slow, patient process, the universe becomes more complex, more varied, and more capable of forming the structures that shape the world. In this quiet way, neutron stars tell part of the human story. Every element has a birthplace, and for some of the rarest and most valuable ones, that birthplace is the merging of collapsed stars in the deep dark of space. The story of the elements is a story of patience, motion, and transformation. It connects the distant past to the present moment, reminding every listener that the matter around them and within them has travelled through processes older and larger than any single world. And so, in the soft glow of everyday life, neutron stars leave their legacy not as distant points of light, but as the fabric of the physical world, atoms shaped by cosmic fire, drifting across time, now woven into the very structure of existence. Neutron stars entered the universe surprisingly early, forming not long after the first generations of massive stars lived out their brief, brilliant lives. In the early cosmos, stars were larger, hotter, and more prone to rapid collapse than most stars forming today. These first giant stars burned through their fuel quickly, living fast and dying young. When their time ended, some collapsed into black holes, while others became the earliest neutron stars. These newborn remnants emerged into a universe that was still settling, still cooling, still gathering its structure. They were among the first dense embers left behind in a cosmos just beginning to define itself. The galaxies of that early time were different from the spirals and ellipses seen today. They were small, irregular, and turbulent, shaped by collisions and streams of gas. Neutron stars formed within them as part of the natural life cycle of the very first massive stars. These collapsed remnants became quiet anchors amid the early chaos. As galaxies merged and grew, neutron stars travelled within them, pulled along by the gravitational tides of newly forming structures. Some survived the mergers intact, held in place by their own staggering density and by their isolation from the disruptive processes unfolding around them. In their earliest era, neutron stars influenced their surroundings not through light, but through gravity and occasional bursts. Young neutron stars often rotated rapidly and emitted strong magnetic fields, shaping the behavior of nearby gas. Their pulses, bursts, and flares contributed subtle but meaningful signals to the early universe, carrying information outward long before planets or complex elements existed. They were part of the story of how early galaxies gained complexity, acting as compact beacons within an expanding cosmic landscape. As time passed, the universe began to change. Stars fused lighter elements into heavier ones, seeding early galaxies with the materials needed for future generations of stars. Neutron stars quietly persisted through this transformation. Their density shielded them from decay. Their compact structure allowed them to endure events that would tear ordinary stars apart. When galaxies collided and reshaped themselves, something that happened far more frequently in the young universe. Neutron stars survived the turbulence, slipping through chaos unchanged. Their small size and incredible mass made them resilient in ways that defied intuition. Across hundreds of millions of years, the universe evolved from a place filled with small, irregular galaxies into one where large spirals and majestic clusters began to take shape. Neutron stars remained through all of it. They drifted through regions that brightened with new stars, passed through clouds of enriched gas, and orbited quietly within galaxies that grew more structured with time. Their persistence mirrored the slow, inevitable march of cosmic evolution, a reminder that some objects are built to last even in a universe defined by change. As billions of years accumulated, neutron stars continued their steady existence. Many slowed their rotations, their pulses stretching farther apart. Their magnetic fields gradually weakened. Their surfaces cooled. Yet none of these changes diminished their essence. A neutron star doesn't fade easily. Its density, its gravity, and its internal structure remain for incredibly long spans of time, even after the stars that formed around them died, even after planets formed and perished. Neutron stars endured, carrying with them the memory of ancient collapses. Their collisions, rare but significant, shaped the chemical evolution of galaxies. Whenever two neutron stars merged, they forged heavy elements and scattered them into space, contributing to the chemical richness needed for later worlds. These contributions happen throughout cosmic time, in the early universe, in the Middle Ages of galaxy formation, and even in the more mature galactic environments of billions of years later. Every collision added something new to the ongoing story, enriching the universe in small but lasting increments. The endurance of neutron stars stands in quiet contrast to the fleeting nature of massive stars. The stars that give birth to neutron stars live short, brilliant lives, ending in moments of fire. Their remnants, however, persist long after the parent stars have disappeared. A neutron star born 12 billion years ago could still exist today, orbiting silently in the halo of a distant galaxy, or lingering in the outer regions of a star cluster. The universe has grown, expanded and evolved around it, yet the neutron star remains largely unchanged. This longevity is partly due to the fact that neutron stars do not burn fuel in the way normal stars do. There is no steady fusion in their cores. Their heat slowly leaks away over immense stretches of time, but the fundamental structure of the star remains stable. It would take something extraordinary, such as a collision, an encounter with another compact object, or the rare possibility of accreting enough mass to collapse into a black hole, to alter a neutron star's identity. In the absence of such events, the star can simply persist, unhurried, for billions upon billions of years. As galaxies age, their rotation slows, their star formation decreases, and their overall appearance shifts. Neutron stars quietly accompany these changes. Some drift into the outskirts of galaxies, where they travel for ages without interacting with anything. Others remain close to stellar populations, continuing to pulse or emit soft radiation. Some remain bound in binary systems, slowly spiraling toward companions or orbiting white dwarfs in long, predictable paths. Each neutron star carries its own story, but all of these stories share a theme of endurance. Looking across all of cosmic time, neutron stars offer a sense of continuity. They link the early universe, with its blazing new stars, to the quieter, more mature galaxies of later ages. They endure through eras of intense activity and long periods of calm. Their existence spans timescales far beyond those of planets or life, yet their influence subtly shapes the universe in lasting ways. They forge elements. They send out pulses that travel through expanding space. They merge, sending ripples across the cosmos that reveal their final moments. Even as the universe ages further, past the present era, past the future when star formation slows, and into the distant epochs where galaxies dim, neutron stars will persist. Their cooling will continue, but their structure will hold. They will drift through space, dim and solitary, long after many brighter objects have faded. Their longevity is a reminder that some forms of matter endure not by shining, but by simply existing in a state so dense and stable that time's erosion becomes slow and nearly irrelevant. In this way, neutron stars become markers of cosmic history. They represent the remnants of early stars, the artifacts of past explosions, and the seeds of heavy elements. They are quiet custodians of time, present from near the beginning and likely to remain far into the distant future. Their pulses may slow, their heat may fade, but their presence continues to carve a path through cosmic ages. Reflecting on their endurance brings a calm perspective. The universe changes constantly. Stars are born, planets form and dissolve, galaxies collide and reshape themselves. Yet neutron stars remain as steady witnesses to it all. They carry within their dense forms the memory of early fires and ancient collapses. They endure through the currents of time, through expansions and mergers, through epochs defined by light and darkness. And through that endurance they offer a gentle reminder of the quiet resilience woven into the fabric of the cosmos. Neutron stars leave a lasting impression not because of their brightness, or their size, or their rarity, but because of the quiet strength they embody. They are what remain after the most dramatic moments in a star's life, shaped by collapse yet defined by endurance. Every part of their story carries a mixture of intensity and calm, from their formation in fire to their long existence as steady, compact remnants drifting through the dark. After travelling through their layers, their behaviour, their interactions, and their role in shaping the universe, it becomes clear that neutron stars are among the cosmos's most patient storytellers, whispering their histories through pulses, waves, and the matter they leave behind. What makes them beautiful is not only their extreme nature, but their balance. They come from violent beginnings, yet they settle into stability. They produce some of the universe's strongest magnetic fields and clearest pulses, yet they emit many of these signals with a rhythm gentle enough to guide astronomers for centuries. They shape heavy elements in brilliant flashes, yet those elements drift quietly into new worlds over immense spans of time. Neutron stars show that the universe often mixes power with subtlety, and that some of its greatest transformations unfold in stages both fierce and calm. Throughout the vast tapestry of cosmic time, neutron stars remain steady. They survive galaxy mergers, stellar births, long winters of darkness, and the slow rearrangement of matter across billions of years. Their endurance gives the universe structure, linking the earliest generations of stars to the galaxies that exist today. They form bridges between explosive collapse and long, slow cooling, between rare collisions and the formation of elements that eventually become part of planets, oceans, tools, and living bodies. All of this places your own life in quiet perspective. You exist in a world shaped by the remnants of collapsed stars. The iron that carries oxygen through your blood was forged in ancient stellar cores. The heavier elements that glint in jewellery or guide electrical currents in your devices were created in the final moments of neutron-star mergers. Even the atoms in your bones have travelled through time, passing through cycles of creation far older than Earth itself. The connection is not meant to overwhelm, only to offer a gentle sense of belonging, a reminder that life is made from the same matter that once glowed in distant stars. After spending so much time exploring the interiors, surfaces, partnerships, collisions, and cosmic roles of neutron stars, it feels right to let the journey settle softly. The physics that shape these stars remain profound, but they do not need to be loud to be meaningful. The universe is full of extremes, yet it is also full of quiet patterns, slow changes, and moments of stillness that stretch across ages. Neutron stars embody all of that at once. Intensity held within calm, pressure balanced by stability, and memory preserved in matter that endures far longer than the stars that formed it. So as this journey comes to its close, consider taking a slow breath, letting the story settle in whatever way feels natural. If you have enjoyed this peaceful exploration, liking the video or subscribing to the channel helps it reach others who might need a moment of calm before sleep. For those already subscribed, thank you for being part of this quiet corner of the internet. Your presence helps these long, gentle explorations continue, and it means more than you might realize. The night will keep stretching out, the stars will keep drifting in their silent paths, and neutron stars will continue their slow, steady existence, spinning or cooling or simply resting in the dark. And you, wherever you are, can drift toward rest, knowing that the universe is filled with rhythms that continue whether or not they are seen. Steady, ancient, and quietly beautiful. May your night be peaceful, your thoughts soft, and your rest deep.